Okay, good morning, everyone. We are at 9:03, so we're a little bit past time that we should be starting. But alas, I want to welcome everyone to day 2 of our amazing TAG-C conference. My name is James Lee. I'm a professor in the Department of Psychology here at UW-Madison, and it is my pleasure to get to introduce our paper session, our first paper session of the day, which is on education. I'm not going to say much because I think that these set of talks are going to be incredibly exciting and interesting for you all, and I hope will generate a lot of discussion and questions for you. But just to say a few words, this set of talks will have to do with incorporating some sort of unique or novel contextualizing lens to better understand the very complex dynamic between our genetics and the educations that we ultimately attain. So without any further ado, let me start by introducing our very first speaker for this panel. It is Shiro Furuya, who is currently a postdoc at Harvard, as well as an assistant professor of sociology at Purdue.
No, this is yours. Good morning, everyone. And this is Shiro Furuya, and I will present something about the interplay between genes and educational attainment. I failed to update the place of the presentation. Like I presented this work last week at the St. Louis at Population Association of America using the same slide, but quite different audience. So I appreciate any comments from the biostatistician, bioinformaticians, or someone not doing certification research. So my primary concern shares with the classic question with the social stratification or mobility research. And if we look at the very classic book of the stratification and mobility, they often ask how much do ascriptive characteristics matter? This is the central question of the stratification research. And my colleagues and I conceptualize genes as one of the forms of the ascriptive characteristics. And for someone who are not familiar with ascriptive characteristics, we can define as like the following. Like traits are ascriptive if those are inherited characteristics given to the individual at birth. And we believe that the genetic predisposition is ascriptive primarily because the genetic predisposition is determined at time of the conception. And also, genetic predisposition cannot be altered over the life course. And in this context, I'm describing genetic predisposition as like the genetic sequence, not the epigenetic clocks or epigenetic mechanism. Just we are focusing on, the sequences like the polygenic index or something like that. So I'm talking this, the interplay between education and genetics, but we are not force groups to think about, or force sociologists to think about the interplay between genetics and education. If we go back to the stratification literature, we can find some description about the interplay between genetics and education, but date back to the 1952. Like the Duncan is a giant in the stratification research, and they refer the heritability of IQ to discuss how much the significance of the genetics in the educational attainment. And more recently, the sociologists began to calculate the twin-based heritability by using the twin data. But with the rise of the polygenic index, we substantially shifted from the heritability research to the regression coefficient. That is quite a conventional way, a conventional shift. But our focus is exclusively on regression coefficients for the educational attainment polygenic index in the regression of the years of education on the educational attainment polygenic index. So this slide is for the stratification researcher, but I want to clarify some terminology in this context. So the heritability is, by definition, is the fraction of the variance in outcome explained by genetic variation. So this is what we. So this I think this is a very appropriate way to test the how much do the ascriptive characteristic matter to address this kind of question. On the other hand, if we look at the regression coefficient represents the average change in outcome, like the educational attainment for every 1 unit increase in the polygenic index. So the regression coefficients include some information about the fraction of variance in outcome explained by the covariates, but this messed up if we are using the multivariate regression. If we are just regressing years of education, educational attainment polygenic index, the regression coefficient works. But if we are using multivariate regression, especially like when we are including a lot of principal components, then the regression coefficient may not represent the fraction of variance explained by genetic components. So in that sense, probably if we look at the R square in the regression, then probably you may draw a different conclusion. And R squared is more aligned with the heritability concept because this is the fraction of the variance in outcome explained by independent variables. So we are trying to do the replicate some previous studies and how the results looks different when we are looking at R square rather than regression coefficients. And our focus on the R square or the residuals or variations can induce more than just R squared. So so the R square is about the top two panels. Like if you look at top right panel, this is low R square because there are a lot of residuals. On the other hand, if we have a smaller residual, we can conclude the significance of the genetics can be high. On the other hand, we can relax the assumption that how the distribution of residuals are different across where you stand in the distribution of genetics. Like if you have very low education attainment polygenic index, probably the significance of the genetics is high. On the other hand, than those who have the high education attainment polygenic index. Or alternatively, if you have very high polygenic index, probably your genetics matters more because you're very gifted. Regardless of the social environment, probably you have a high educational attainment, regardless of the social environments. So by looking at the residuals, we can infer way more than just a regression coefficients. And we are trying to do this kind of analysis. So our goal in this project is like we calculate how much polygenic index can explain the variance in educational attainment. As I mentioned, I will report to a paper, influential paper in American Sociological Review published in 2019 by Wisconsin colleagues Pam Hard, and they show the gender difference in the regression coefficient and how that differ when we look at the R squared. And we will also examine not the gender at this point, but in this presentation, I will examine how the residuals are distributed over where you stand in the distribution of the polygenic index. And by doing so, I would like to make some inferences on this, broader question in the stratification research, like how much do ascriptive characteristics or genetic predisposition matter? So our data and sample are following as I mentioned, the Pam Hard ASR paper, but we are using Wisconsin longitudinal study and also health and retirement study. They also use other health, but I applied the restricted data, but still I have not received the approval, so I could not do the analysis for the other health. But we could do some analysis with WLS and HRS. And PGI are publicly available, and it's easy to access to these kind of genetic data. So our analysis, well, yesterday we had a lot of fancy equations, but my analysis is very simple. Like we are just regressing years of schooling as an outcome on polygenic index. This is education attainment polygenic index provided SSGSE, and with some covariates such as the first 10 genetic principal components and sex and the Barcia fixed effect that is only for the HRS. And so in the Pam Hard's paper, their focus is alpha 2 in this equation, but we will calculate the partial R square for the PGI. I'm mentioning the partial R square to isolate the R square for the PGI, not just entire equation. So I will try to mitigate the impact of the first 10 principal genetic principal components or the covariates from the R squared. And for the distribution of residuals, we are modeling we allow to change the error term by the Poisson index. And so the blue font shows the how we model the error term, and we can take the variance of the residuals to understand how the variance will differ by the Poisson index. And this is a kind of application of the ideas of the multi-level model, but we are still focusing on just an individual level, not the more aggregated level. So this is the kind of replication of the Palmer-Hart's paper, and the WLS, as they found, like with the Wisconsin longitudinal study, we also found the very clear and the significant gender differences. So the males have the more steeper slope, like their regression coefficient is higher than females, and this gender difference is statistically significant at the 1% level. And their conclusion is like, based on these results, the genetics matters more for males than females. And for the HLS, I could not find any gender differences by just looking at regression coefficients. And then we calculated partial R squared. And although we found the clear gender differences in the regression coefficients, I did not find the clear or significant differences in R squared between males and the females. This implies that although there is a gender differences in regression coefficients, the deflection of the years of education explained by Poisson index does not change or vary between males and females. So in that sense, to less likely how much do the genetics matter for the educational attainment for males and the females, probably their conclusion, we have somewhat different conclusion. Like there can be no gender differences in terms of the significance of the genetic role in the educational attainment. And we do not find the gender differences with the HLS. And so this is not about gender, but we can move on to the analysis of the residuals. So the major takeaway from this, so the red line shows the mean, the expected mean, and the shaded area is not a 95 confidence interval. This is just a standard deviation, expected or standard deviation of the years of schooling based on their Poisson index by using the regression equation that I use. So the major takeaway from this figure is there are less residuals when you have low Poisson index than those who have high Poisson index. In this context, like probably the genetics may matter more for when you are among those who have low genetic educational attainment, low educational Poisson index, and those who have high high education Poisson index, because there are less variation in terms of residuals among those people in this side. So this is based on the Wisconsin longitudinal study, and I can replicate this finding with the HLS. But our focus is the high school level or those who completed compulsory education, because Wisconsin longitudinal study follows those who graduate from the high school in 1957 or sometime. So we could replicate the findings, but if we focus on the less than high school, there are somewhat different stories. Like if you have low education Poisson index, there are more variation in terms of residuals than those who have high education Poisson index. We are somewhat struggling how we can explain this kind of discrepancy between these two education groups. But so, any comments are very much appreciated after this presentation in the QA or after the discussion in the lunchtime on the networking event. So I would like to wrap up my presentation with some take-home messages. So a lot of sociology or social science research exclusively focus on regression coefficients, but differences in the point estimates may not imply the difference in the strength or significance of the role of genetics. In that sense, we want to, look at not just the regression coefficient, but probably the the standard errors or a standard deviation or R squared or distribution of residuals. And the importance of genes probably varies across the distribution of the genetic predisposition. So underlying assumption of the polygenic index, the research on the polygenic index, like the homoscedasticity, like we are assuming the equal importance across where you stand in the distribution of the genetics. But probably this is a implausible assumption because some genes matters more than the other genes, genetic characteristics. So we can relax to some underlying or implicit assumption by taking the, by allowing the error term can be vary across the distribution of the PGS. And this is the final slide. And thank you very much. And any comments? I highly appreciate it.
So it's very interesting talk. So your model looks very similar to the double generalized least squares that people use for VQTL detection. And in that context, if you see anything significant that would imply gene environment interaction, so here it appears to me that part of the heteroscedasticity could be explained by potential interactions between your PGI and unmodeled environmental or lifestyle factors. So have you considered?
Yeah. So I'm not presenting so I can check this kind of the theoretical argument by looking at the kind of educational attainment, but not the years of schooling, like the reading test scores. So when using the reading test scores, there is no heteroscedasticity. There is just homoscedasticity. One possible explanation is like the compulsory education. So even if you have very low education, genetic potential to achieve certain level of education, the compulsory education may boost up their educational attainment. Therefore, there are less variation among those who are low education polygenic index. So that is one possible explanation that I can think of at this point. But yes, the social environment may change the importance of the genetics, and there is a pretty this can align with the context of gene by E interactions. I think. Yeah.
Thank you.
Thank you.
Thank you so much for the research. I think, yeah, I can't wait to cite this for my for my dissertation project. Like again, it's very important, and I think we should definitely do more of those kind of research to really explain, try to explain what to make of the polygenic scores that we use. So yeah, thank you so much for that. And I guess my first question is like related to what you just said. I totally agree that because of a compulsory education, probably because especially in the U.S. Although, like, I guess in different cohorts means slightly different things. But I just wondering, like, how have you tried, like, trying to remove that, like, the whatever years of compulsory education was present at the time of those cohorts going to college or going to high school, and then just looking at the rest and see what the variance is like in those kind of parts.
So Wisconsin longevity, I think we cannot do that kind of analysis because we are selecting based on their sample is like those who graduated from high school, but in the probably HLS have some information like because there's presumably they're not computing there are some observation for not computing the compulsory education due to the age computed at the highest education, something like that. And when using other health, probably we can do more, but it's very unfortunate that at this point I do not have the results that I can present, and I do not know any findings at this point. So TBD. I'm happy to inform once you have some results with other health or some other data sets.
That would be fantastic. Yeah, thank you so much for that. And then the other question is like more practical for researchers like us trying to use educational attainment, PGI, and trying to cite your paper. Like, what do you suggest that we do in terms of like, should we just do a better explanation of the limitations and what to make sense of that, or are there like some systematic changes to the way that we use the PGI that you would suggest?
So my suggestion is like try to understand every single numbers on your statistical softwares. Like I don't know, this is probably not right answer, but this data or whatever, we have a lot of the numbers in output in the regression outputs, but usually we disregard most of the outputs. Like we do not interpret the constants, but to understand like the variation and residuals, these are pretty close to the concept of the constant. What is the mean values? What is the constant implies? So probably we have to, the sociologists probably should pay more attention to every single numbers and what these numbers represent. This is a kind of the argument about what is your estimate. Like we should have the research goal and we should select appropriate number to test your research question. And I think our careful attention to this kind of issue is quite important for the social science.
Awesome. Thank you so much.
Thanks.
Thank you, Shiro. All right. Our next speaker is Seward Van Alten from VU Amsterdam.
Thank you. Okay, hello. Welcome back. I'm happy to be talking to you guys today about this project on the externalizing behavior of parents and its effect on the human capital of children, which I research using genetic data. The idea behind this project is that as an economist, I am interested in the intergenerational transmission of economic traits, of income, of human capital, which is econ speak for educational attainment in a sense. And we can imagine that the reason that human capital is transmitted from generation to generation is because children develop themselves in environments that are created by their parents, right? So if I ask myself the question, if my father is higher educated, then I am more likely to become higher educated myself. Why is that the case? Because my higher educated father somehow possibly creates the environment in which I develop those skills, right? Now, there is a very large literature in economics examining the intergenerational transmission of human capital, but it mostly focuses on the resources that parents have. So you get questions about father has a lot of human capital, father has a lot of income. How does that affect the children, right? But that's plausibly only one dimension to which parental traits matter in shaping the economic outcomes of the next generation. And we think that behaviors in the economic literature have been quite undervalued in terms of and being under-researched in terms of its effect on human capital outcomes, even though, of course, behaviors of the parents, how the parent interacts with the child in various situations could be very important in how the child develops its human capital. And in this paper, we will specifically focus on externalizing behavior, which in psychology is this sort of broad factor that explains people's propensity towards antisocial tendencies, problems with attention, and that could result in things such as substance use, lack of emotional regulation, etc. Right? So I think in the literature of psychiatry, psychology, externalizing behavior takes quite a central place. Nonetheless, in economics, I'd say that if you look at economics papers mentioning externalizing behavior, you almost find nothing. So it's been fairly under-researched there. Nonetheless, if you look at what this behavioral spectrum does, I think you can already hypothesize that this affects how, if a parent has a big tendencies of that externalizing behavior, how it affects how it interacts with the child and so on, and therefore affects the children's outcomes, right? So that's the question that we will ask. How does the externalizing behavior of one generation affect the education and income of the next generation? Now, how do we research that in this paper? Well, first of all, we recognize that insofar as the literature researches the effect of parental behaviors on economic outcomes of children, there's not so much there, and whatever is there is purely associational. So you get some measure of parental behavior, it associates with children's human capital, right? It's of course very difficult to get there from a cause, an association to some type of causal effect. So we were thinking with genetic variables, with polygenic indices, if we condition it within family, we can estimate some type of causal effect of these polygenic indices, right? So let's take it as a starting point. Let's start to do that, and let's start to think about if a parent has a larger genetic propensity to externalizing behavior, what is the effect of that larger genetic propensity on the human capital formation of children, right? That is a causal effect that we can estimate in the sense that there is a clear counterfactual there. What if the parent at conception inherited different genes such that it would not have this large tendency to externalizing behavior, right? But as you probably know, what is very difficult with interpreting the causal effects of polygenic indices, yes, they are causal, but why are they causal, right? What are the various mechanisms through which they elicit their effects, right? So in that sense, what we do in this paper is we don't try to say like the causal effect that we estimate goes exclusively through externalizing behavior. It could go through other behaviors, but nonetheless, what we do show is that the effect of the externalizing PGI, it does not have a substantial effect on the human capital or the labor market outcomes of this parent. So if you see that the externalizing PGI of the parent has a large effect on the human capital of children, but nonetheless the externalizing PGI of the parent does not have a large effect on the labor market outcomes of the parent, right? Then the reason that that large effect is there must be through some other mechanism, right? And we are going to scrutinize that further, and we're going to sort of come to the understanding that whatever is the large intergenerational effect of the externalizing PGI that we estimate, that it's mostly consistent with going through various behaviors, which shows that behaviors of parents in a broad sense are very important in shaping the human capital of children, right? And so that's we think of that causal effect as something like a basket of features, right? Like the externalizing PGI influences who the parent is in the broad sense, and that's as causal as we, or sort of that's as deep as we can go in understanding that effect. Nonetheless, I dare say that that's fairly similar to any type of causal paper in the literature on the intergenerational effects. So even if you have, say, a clean identification strategy for education, so maybe you have a raising of the schooling age of the parents, and therefore the parent went to school for longer, you could then measure a causal effect on the education of children, but this could go to a whole bunch of mechanisms, right? And similar things with adoption studies and so on. So that's the type of sort of effect that we estimate here. And overall, I'd say that we are the first paper in economics that tries to estimate some type of causal effect related to parental behaviors beyond parental human capital and its effect on children's development, therefore showing that parental behaviors matter a lot. The data that we use for this project is similar to what you saw presented by some of my colleagues yesterday. That is this Lifelines cohort we have in the Netherlands, a very large biobank with a lot of genetic data. But second of all, we can link it to administrative data such that we can see economic outcomes of these participants, but also their children. And on top of that, in this project, we also used the fact that this study has quite rich survey data, both on health and mental health, but mostly to capture externalizing behavior, the effect of behaviors. So you'll see quite some of that survey data today as well. And then how do we capture externalizing behavior? Well, this has been researched in the genetic literature quite substantially. And I think the best way that we currently have to capture some type of genetic propensity externalizing behavior is this idea of this GWAS by Linner et al., who recognize that externalizing behavior is some type of latent factor that could result in various type of behaviors related to substance use, related to risk-taking, related to lack of emotional regulation. So what they do in the end is similar to that idea. They say like, okay, we can GWAS 7 different outcomes that all relate to externalizing behavior, and using genomic SEM, subtract the latent trait, which we then label externalizing behavior, right? Once you have done that, it's as if you have done a GWAS on the externalizing behavior trait itself, which is latent, so you can't observe it directly, right? And what are these 7 GWASs? It's number of sex partners, smoking, alcohol use, ADHD, cannabis use, frequency of sex, or no, age of first sex partners, and risky behavior, right? You can debate all you want whether that's the best way to characterize externalizing behavior. Nonetheless, I dare say that this is sort of the best we can do given the literature, right? And then it's as if we have done a GWAS on externalizing behavior, can use that to create the PGI, right? Which I would characterize as the best linear genetic predictor for externalizing behavior given the literature. So before I show you how that PGI affects, first of all, the parents inheriting these PGI, and then next, the children that they later on get. As you know, we should never estimate naive associations between PGIs and outcomes, especially when studying socioeconomic status and so on, because we might have confounding, right? People don't just inherit genetic variables from their parents, they also inherit environments from their parents, making everything correlated. And that's why we need a more credible identification strategy than this naive idea. So here the naive idea is simply, let's look at the association between the externalizing PGI and some outcome. And to show you that that's a stupid idea, here I have various outcomes as measured in the parents of the people who inherit the externalizing PGI, right? And what we can see is that people with a higher externalizing PGI, they also report that their mother was more likely to smoke, father was more likely to smoke, their parents were more likely to be addicted to something, but also their parents had lower socioeconomic status in terms of as measured as their net wealth. Yeah, so that shows you that there's confounding going on. These PGIs, they are not clean measures separated from the environment. They predict the environment that people have grown up in, right? But what is the identification strategy to make that more credible? As you know, we'd have to do something within family, and what we do here is we control for the externalizing PGI of one's parents, and that makes all these effects go to zero. So now we can no longer predict backwards from the externalizing PGI, but as I show, we can still predict forwards, which we then interpret as causal effects. So yeah, first I'll show you what the inheritant and externalizing PGI, what the causal effects are of that on various behavioral outcomes, outcomes related to substance use, and outcomes related to human capital. In the generation, which will be the generation of the people that are lately in the intergenerational analysis we'll call the parents. Yeah. So what do those results look like? Well, here you see that the externalizing PGI, if you have a 1 standard deviation increase of it at conception, you're more likely to report hostile behavior, a 0.09 increase in your standard deviation of reporting impulsive behavior, but also quite substantial higher likelihood of engaging in all types of substance use. And I'd say that these are very substantial effects. So the mean of any drug use is 10% in this data, but a 1 standard deviation increases it by 3%. I think these are among the larger effects that I personally have seen for behavioral PGI. So this PGI is very predictive of the types of behaviors that we like to think affect externalizing behavior or are related to externalizing behavior. Right? And these are causal effects as well. And then, but how does it influence people's own labor market outcomes and human capital? And here we see very limited and no statistically significant effects, which we were fairly surprised by. Because a lot of literature feels like if people have a lot of externalizing behavior, they wouldn't do so well in the education system or the labor market. Yet it is fairly limited. And then we go to this intergenerational analysis. So now we have given the parents, we know that they have given some type of exogenous treatment, and it mostly affects their substance use disorder, it mostly affects their impulsivity, hostility, but it doesn't affect so much their labor market outcomes. Now the next question is, what happens to their children, right? So we just take the same equation, but we swap for outcomes as measured in the child of these people, which we can identify using the administrative data. And we do see here that there is a big negative effect on the years of education of these children and their likelihood to go to university. So these effects, these intergenerational effects that you see here, are much larger, minus 0.15 years, as compared to what you saw in the generation of the parents where it was barely affected, right? And we think that is a very interesting pattern in the data because it basically shows you that this intergenerational effect, it really affects the years of education of the children, even though it does not affect so much the years of education of these parents, right? And here is basically that is visualized. I flip the sign to make the plot look nicer. We see that the parents' generation is barely affected by inheriting a larger externalizing PGI, but the children of these parents, they have lower education, right? So you have this increasing intergenerational effect. The intergenerational effect is larger than the first generation effect, which I say in the economic literature on intergenerational transmission is quite unique. Usually it affects the first generation and maybe the second generation a little bit. which is, for example, what you see for the EA-PGI, right? Where also the first generation, the second generation is affected quite a bit. So that's this other working paper that we have on that. But it does decay, whereas this does not decay, it increases in the next generation. I think my time is almost up, but we do quite some additional analysis to really understand the mechanisms there. So the first thing we ask is, why are these intergenerational effects so large? Is it because these children inherit the genes from their parent, or is it because the parent has genes that affect the environment of these children? And we do a mechanism analysis there, and genetic transmission cannot account for a lot of this effect. And I think intuitively that makes sense, because the effect of your own PGI for externalizing on your education outcomes is not that large in the first place, right? So that's how that analysis works. And then we also do some things with partner choice, but we don't see very big effects on who these partners are, so it doesn't account for much. And also we're working on a sort of fertility correction, but that also does not account for these big effects. So that gives us with sort of the last guess is that the reason that these effects are so big is because these parents, because of their large externalizing PGI, behave fairly differently and behave in a way that it's not so good for the development of the child, right? Yeah, so that's sort of how we interpret these results. Well, what does that all mean? I think that despite it being an externalizing PGI causal effect that obviously aggregates a lot of behavioral mechanisms in the parent, I think it is clear evidence that behavior of the parent matters for children in some type of causal manner. It's also a rare case where the intergenerational effects of the treatment in this case being the externalizing PGI, exceed these first generation effects for labor market outcomes. So that also shows you that whatever are the skills that are related in the labor market by employers are not necessarily the type of skills that are the best skills to increase the human capital of your child, right? And of course, in terms of policy intervention, well, this is a type of treatment which is genetic. We typically don't think of genes as something that we would intervene on as a government or whomever, right? But nonetheless, if we talk about externalizing behavior, psychologists and psychiatrists do consider that to be malleable in itself. So it also shows you that if you look at the effects of externalizing behavior interventions to reduce your externalizing behavior, and you want to understand if those interventions are cost effective, that you shouldn't necessarily look at the outcomes of the people who are taking that intervention, but you should also take the outcomes of their children into account, right? Because that might actually be where the effect is that is at least good to the economy, right? So that's our conclusion, and very curious to learn what you think about all this. Thanks.
Thank you. That was very interesting. I guess I have two hypotheses to ask about this difference in effect on the focal person's outcomes versus the children's outcomes. And I guess one hypothesis is about the timing of the externalizing behaviors. If the externalizing behaviors PGI is developed on sort of later adulthood externalizing behaviors and not early, say, adolescent externalizing behaviors, then perhaps the PGI that you've estimated isn't reflective of the externalizing behaviors that are maybe most crucial for human capital development. So that's the first hypothesis. Second hypothesis is maybe externalizing behavior, it isn't about my externalizing behaviors, but rather about my parents' externalizing behaviors that affects my human capital development. So when you look at my externalizing behaviors on my outcomes, you don't see a relationship. But when you look at my externalizing behaviors on my children's outcomes, you would see a relationship. So really, maybe you're interested on people, you can't do this with your identification strategy, but you might be really interested in what are the parents' externalizing behaviors causal effect on the focal person. Anyway, two hypotheses that I thought of, and I'm interested to hear your thoughts on those.
Yeah, thanks. So regarding your first one, these children are at least 25 years old, right? So their years of education has been completed. And as a second check, we also look at income and we see very similar results. Then you might, of course, still wonder, like, okay, to what extent does it bias the analysis that the parents are quite a bit older in this analysis as compared to the children, right? Although we do shift the years as much as possible to sort of mitigate that issue, right? And then as an additional check, we did a lot of testing for like birth cohort trends in the data to see like, is the externalizing PGI more predictive for certain birth cohorts, right? Because that indeed could make this intergenerational effect, the way we analyze it, more complicated. But I've been trying to do that quite flexibly in terms of year of birth trends. There was not really a way of getting any type of big or statistically significant effect. So it seems to be that the externalizing PGI in our data is quite predictive for every single generation, as long as we measure the outcome once adulthood has been reached. So that's my thoughts on your first hypothesis. And I forgot what the second one was. I'm sorry. My, as in you're the. Yep. Ah. Mm-hmm. Yeah, but in a sense, I think that's what we are showing. And then you can, of course, always wonder, like, okay, if the GWAS would have been done in different data, would we have constructed a different type of PGI for externalizing behavior, right? But I think that's exactly sort of the point of our paper is like, if we at least construct the externalizing behavior PGI in this way, then we get something that is very consistent with your own externalizing behavior being affected, or at least its consequences of it, right? But the next generation children's labor market outcomes being affected, right? So if that's the treatment that I give to the data, then those are the causal results that I get from the data, right? And of course, if you would construct your PGI differently, at least hypothetically, maybe all those mechanisms could change subtly, right? It's something like, okay, if you're weighting the genome in this way, then these are the patterns that you find, right? And that's consistent, but to me, that's consistent with behaviors of parents indeed mattering to human capital, right? Which is also sort of your second hypothesis. Yeah.
So I have a hopefully really quick question for you before we move on. There are pretty drastic sex differences in terms of the expression of externalizing psychopathology at the phenotypic level, that is. So I'm just curious if you looked at the differences between mother and father, since I see that you just presented on parental. So can you comment on that?
Yeah, so indeed people do ask about the gender differences. So that's what I started looking at. And what we see is indeed that for those first generation results, it seems that if you do those in men, that the PGI is more predictive for most outcomes. So that means, of course, that everything that I've shown you should be split up by gender of the parent or gender of the child. And I was working on that, but then the Central Bureau of Statistics caught fire in the Netherlands. So I hope that will be resolved soon. But this is definitely the next step, the first thing I'll do once I can get back to it. Yeah.
All right, another round of applause for Stuart. Thank you. Okay, and our last speaker is Boyan Zhang, who is a postdoc at Harvard, right? Or Princeton, sorry, Princeton.
Yeah. Okay, let me open my. Mine is here. Are you okay? Yeah, thank you very much. I'm very happy to be here to present my research on the gene-back cohort interaction effects on educational attainments. Currently, from the US data, we want to do the UK Biobank eventually, and this is a collaborative work with Yucheng, Q, and Jason. So let me go back to the question Silo had raised, the issue of how genetic affects educational attainment. That is really the question that is of the central focus of sociologists of my field. And there are three ways to frame that questions, because given that basically cohort means social economic developments or other similar things, there are three views. The first view is that as time goes by, the genetic effects will be stronger because there is what we call a equality of opportunity that improves the meritocratic selection of children's endowments or abilities, and so that as society becoming more open, the people could express their endowments, and the genetic effects on education just become stronger and stronger. An alternative explanation, however, is a weak genetic effect assumption. It considers the societal change as not changed by the equality of opportunity, but changed in the openness or the absolute of availability of opportunity to all social groups, so that the selections on meritocracy or endowments, the hypothetical mechanism of genes is less and less important, so that the genetic effect becomes weaker as well. And third, there is also a non-hypothesis, just like the strikingly stable social mobility in US and around the world. There's just no change in so-called the education genetic effect at all. And there are evidence on all directions in influential publications. This is one of the paper. Silo also has cited Palmer Hard's paper, like using the 10,000 cases men and women in HRS. These are PGS coefficients. They basically say that, oh, the men's genetic effect declined, whereas the women's are increasing, and they interpret this increasing as because the educational opportunities is more open to women's talents for later cohorts. And there are also influential evidence of so-called weak genetic effects at least in the context of sociology. This example comes from a very recent publication in our top journal, using only 2,000 cases, showing that after the UK education reform, the blue line, the PJI, the PRS by education gradient become weaker when an education reform of the rising of the school leaving age is introduced to UK. The third evidence is another paper on, I think, sociological science. They basically show that there are some trends, but not really much. And the association between genetics and destination by education just appears to be fluctuating without clear trend. There are all kinds of mixed evidence. So why the mix? Why the evidence is mixed? One thing also mentioned by Silo and I briefly discussed in my previous paper is that some evidence is based on heritability and others are based on the PGS coefficients, and they can be interpreted in vastly different ways. And particularly, heritability can decrease even if there is no change in PGS coefficients, simply because the exogenous unrelated variation of the phenotype is decreasing. The other issue is the sample size, I will show. The third issue is the theoretical framework, which is the direct versus indirect PGS effects. Let us briefly go through the sample size issues. This is the 2018 Nature Human Behavior, a very influential paper in the field. It shows that in using a sample of 10,000, it shows that after the collapse of Soviet Union, the heritability estimate of the genes on education become twice as large. Compare this bar to this bar. They treat this as evidence that the collapse of Soviet Union increased the equality of opportunity and allow people to express their endowments and therefore larger genetic effects. Although this is very influential, in a recent working paper using Estonia Biobank, I think very uniquely capture almost half of the population. They show that, and using a 200,000 sample set, they really show there's no clear trend at all. Just a fluctuating genetic coefficients by cohort, and there's no evidence that the Soviet Union, the collapse of Soviet Union make a sharp change in genetic effects. The other issue is how do we interpret genetic effects or PGS coefficients? Many colleagues yesterday talked about indirect and direct effects in a causal mediation sense. And in the field of genetics, the Alexander Young has this language of indirect effects in a different sense. The direct genetic effects are biological endowments or gene-driven differential parenting. It basically say how the parts of genes in my own body affect my own outcome. And they kind of translate to what sociology called achieved factors, ability, or other things. And the indirect effects in this framework refers to how the surrounding similar genetic environment shape my outcomes. The prominent example is the parents who share my gene, and the genes shared by my parents affect, like how, for example, how educated my parents are, and how my parents would invest me material and non-materially, like the idea of genetic nurturing. And these indirect effects also account for the overall PGS or PGI by phenotype correlation. And from a sociological thinking, they may change very differently, because what we call the intergenerational mobility is most, when we say intergenerational transmission, we say there is a parents cultivate children's ability, that's meritocracy, where parents' investment in children's educational attainments, that's non-meritocracy. And in a society where, if we assume, for example, the society becomes more open to opportunities, regardless what happened, we may say both the parental investment and ego endowments should have weaker effects. Or in other sense, there is an equality of opportunity that only selects children's endowments, but make parental background less relevant, net of children's own abilities. We may expect the direct effect goes down, but the direct effect goes up, but the indirect effect of genes through parental treatment goes down. So there could, if we really try to disentangle the indirect and direct effects, we may got some different insights and better test of our theoretical hypothesis. And another goal of the present research is to draw a larger sample size from all of us to gain more powerful evidence of gene by cohort interactions. So let me go briefly about the research design. We use all of us, and the eventual sample is around, I think, 300,000 European ancestry in United States. The key outcome is education, years of schooling, and the covariate is just the principal components, and we will do cohort by gender specific analysis. And all of us is not representative, so we construct a reweighting based on the immigrant membership, the resident region, and other demographic factors to match all of us to the 2018 to 2022 ACS, which is the period when the data are collected to try to see whether the selectivity or the simple representativeness really affect our interpretation. And to disentangle the indirect and direct genetic effects, we basically using the approach, we using how adult summary statistics who construct the weighting sibling PGS by taking the random variation of genes between the siblings to construct a direct PGS. And meanwhile, the Yu Chang, my collaborator, has a wonderful proof showing that if we subtract the direct GWAS from the population GWAS, the remaining GWAS can be used to construct a PGS that capture the direct genetic effects or the genetic effects of how my parents' gene affect myself from their achievement and behavior. And then we can jump to the findings to see what's going on. So this is updated evidence of the United States of indirect and direct PGS coefficient. If we make some causal interpretation of this evidence, there are two major conclusions. First, we actually see that since the post-war cohort, the genetic effects of indirect and direct effects both increase. And the indirect genetic effects are actually larger than the direct one. And it highlights that when we're talking about how genes affect my outcome, that is probably not so much about my biological endowments, but because how achieving my parents are and the degree to which my parents' genetic-driven parenting behavior can shape my development. That is kind of a new finding here. And also this increase in trend also kind of go against the earlier studies, but we will check the gender pattern later. And that's sort of supporting a strong genetic effects, which vastly contrast the declining PGS coefficient in the UK context. And there is a slightly decline, but hard to interpret here. And if we contrast that with the marginal educational attainment trend, we show that this increase in the genetic effects appears to be more in line with the increase in college education supply in the United States. So there are some evidence that the increase in supply is more aligned with the equality of the opportunity thesis rather than the openness or the availability of educational chances thesis in the United context. If we further look at the gender differences, that contrasts with the earlier American Sociological Review paper, it doesn't really show that the different genders show different trends. They kind of both increasing, and the degree of increase is actually larger than males. You can see going from a relatively lower point and becomes significantly larger than females, at least for the 1960s. I mean, the reason is not very clear, but it challenges the previous findings and show no gender differential trends. And finally, we just briefly contrasted the weighted and unweighted estimates. The weighted estimates is we forced all of us to have the same distribution of the ACS. And really the trend doesn't change very much except for the pre-war cohort, the World War II cohorts. And for all the subsequent cohorts, there is a shift up of the coefficients for all cohorts, but there is no systematic transition in trends. We still see an overall increase in genetic effects in the United States, and in UK is decreasing. So there's a brief conclusion and the discussion. We do see effect-specific trends, but overall the indirect effects are larger. Both increase to some degrees, and since the 1980s, there is a stable or slight decline. But there is no evidence that the two effects are diverging. They move in the same direction. And they kind of following a meritocratic transition pattern, saying that the selection over genetic-driven either endowments or parental backgrounds becomes stronger in the US. And so they educate that. And regarding gender differences, we do not have evidence that men and women's genetic effects, either direct or indirect, move in different directions. And the men appear to have far larger increase. And the main important difference between our research and Palmer Hart is that our sample size is 30 times larger. And here I want to note again that the power really matters if you want to do gen by cohort interaction analysis. And a discussion, we want to do a formal decomposition of total genetic effects into the direct and indirect ones. And Yuchang has developed the formula, and when there's a time, we will implement the analysis. And we want to understand the mechanisms if there could be some data. Yeah, and that's all for today. Thank you very much.
Very, very interesting work. So I'm interested in the age distribution of all of us. So from 1940 to 2020, that's like 80 years old, and it's substantially longer than the current average lifespan of American people. So I know you have some adjustment for the the difference between the study population and the general population of the U.S. So can you comment more on that? And would that influence like the sex or gender specific pattern, because women have a longer lifespan?
Yeah, thank you very much. That is that do leads to concern that, particularly based on the weighting results, it looks like to include the pre-1940 results seems to really make a difference, because you see the weighting doesn't just doesn't change the over 80 years old respondents. So I agree that there should be a difference. But for the later cohort, like who are under 80 years old upon the survey time, the weighting doesn't change quite much. That's one perspective. And regarding the mortality selection, the Domingo has a mortality selection weight for PGS for the HRS, and that doesn't change quite much of the analytical results. So it gave us some indirect confidence that maybe the mortality doesn't matter for the people who are under 70, under 80 when they are surveyed. But as you suggested, we should probably do some left table adjustment. I mean, if the genetics have a direct effect on mortality or education PGS directly affect mortality net of individual attainment, there could be a collider bias that maybe downwardly affect the earlier cohorts. There is a risk. We will try to evaluate. Yeah, thanks.
Thank you. This is very interesting. So I have one comment or suggestion. Yeah. I noticed you use like the Hall et al. For within sibling jewels, but I guess like there is a more recent one that is 10 et al. So basically, I think they also use different strategies in order to get this like jewel summary statistics. And the reason I think like a limitation with the Hall et al. Is that they include very low imputation quality SNPs. So that might not like follow the Mendelian inheritance pattern. I think that's like empirically validated by, I don't know, like a certain team already. So like I guess like shifting to another more recent GWAS might help a little bit. And another more like a question is that because you are doing like a G by cohort interaction, and I think it's very natural to think about like the portability or the prediction accuracy in this term in this case. So like if the education GWAS was trained in a certain birth cohort, maybe it's naturally less predictive or like less predictive accuracy among other cohorts. And I just like wonder how you think about this case.
Yeah, thank you very much for your suggestions. Regarding the first question, yeah, thank you. I don't really know. I will check. Yeah, I don't know that new GWAS. I think we should probably use that to gain more statistical power, because you see the coefficient on education here is only kind of half or 1/3 of the EA4. Yeah, so we can, it would be great if we can use a more powered GWAS. And regarding the portability, so for example, the big part of the sibling GWAS of Hall et al. Is UK Biobank. I mean, 30,000 comes from the UK Biobank, where their birth cohort is about 40 to 60. Because that is an old cohort. So if everything is driven by portability here, then the older cohort should have larger coefficients, because they really maps the age of the UK Biobank or other older adults-based biobank sibling data. So based on that pattern, I think the portability should absolutely matter, but that would not qualitatively change the finding here. I mean, the increasing, because if the portability is everything, I think we would expect a decreasing of the genetic coefficients.
Okay, thank you.
Thank you. You cited two papers about the post-Soviet finding with mixed findings, but I think the methodology was different, right? One was reporting heritability differences. Another focused on polygenic score coefficient. And here you're choosing to report PGS coefficient. I wonder if I can comment on the decision.
I mean, the later paper do both. So I draw the heritability estimates of the later paper. Yeah.
Yes. So, but here you're not reporting heritability differences. So I wonder what's the decision here. And the second question is maybe a follow-up to the previous comment. I think it may be useful to plot a scatter plot. The x-axis being the GWAS sample birth year distribution. And the y-axis being the coefficient you actually obtain in different year. So you can see if there's a direct correlation of overrepresentation of people coming from a specific birth year or specific birth cohort, if that is correlated with the larger coefficient you are seeing in your analysis.
Yeah, thank you for the suggestion. I think I will do. Yeah, for this comparison, this is just the I pragmatically draw these two results because as far as I know, this is only quite useful contrast of how sample size could change the conclusion. And I personally do not find a very direct, say, the PGS coefficient-based replication that show like the cohort trends are really different. this is pragmatic. To be honest, and the reason I do not do heritability is that practically the heritability could be changed by exogenous shift in the phenotype variation that is not related to gene. So I personally do not prefer heritability as a very clear interpretation of the genetic coefficients. So I would, So I think the marginal effects of PGS coefficient has a more comparable interpretation regarding how genes should affect population educational distribution. That's my purpose. But I'm surely open to the discussion regarding whether the heritability could offer similar conclusion. Maybe I should try. Thanks.
All right, let's give another round of applause to our speakers. And then we're going to take a break until 10:30, and then we'll have our next session after that.
So every year we get submissions that don't fit in education or what were our other ones, families, and they're just often big picture questions. And here I just labeled it science. So this is a nice one to wrap up before our great upcoming keynote. I'll let Bennett take over, and we'll keep time.
Thanks, Jason. Can y'all hear me? There we go. So I'm Bennett. I'm in the History of Science program and the Science and Technology Studies Center here at the University of Wisconsin. So in addition to the Social Genomics Institute, we've got a lot of folks who do social studies of science, and you heard from one of them yesterday. I'm going to talk to you today about what it is that scientists and critics of a certain science, your science, mean when they use the phrase social construction, what kind of social function that's playing, especially when it comes to the idea that race or ancestry categories or other ways of carving up populations are, quote, socially constructed. It's kind of funny giving a talk to an audience like this because I have to kind of invert my literature analysis and my empirical portion. The bit that I'm telling you that you already know, how and why social genomics uses race, is usually what I would say second in my papers. The bit that I'm telling you that you may not already know is usually what I would say in my literature review. But the way we're going to do this today is talk a little bit about some of the terminologies that genomics generally and social genomics in particular uses around race and population categories, and what specifically the function of calling those categories, some of those categories, especially race, a social construct is. And then I'm going to introduce another way that people talk about race as a social construct. Often in content, it's a very similar kind of description, but the role that it's playing socially is very different. And these are people who are kind of coming in, historians, sociologists, sometimes philosophers, coming in from outside of the field, criticizing social genomics by saying, no, not only race, but also biostatistical classifications are socially constructed. My work is usually very descriptive. But you had such good questions last year when I came to talk about, well, what should we do given that I have presented this historical narrative to you? So I'm going to foray into some normative philosophy of science, bring in the philosopher Ian Hacking's notion of humankind's and looping effects for a bit of a discussion at the end. A bit about what I do. I'm in a history department, but I'm as much an ethnographer of science as I am a historian. I'm very interested in how scientists make meaning out of the data, out of the tools that they have available to them. And I also think when studying this, it's really important to be reflexive. That is to say that it's important to understand how I'm interpreting and making meaning out of the data that I have, interviews with you, the papers and methods and trade books that I read, and also that I examine how I'm acting at conferences like this and check my work, make sure that the narratives that I'm coming up with at least somewhat match your experience of what's going on in the science. So this may not surprise any of you. There's a lot of discussion about how geneticists should talk about race, ancestry, genetic similarity. This dates back a long while. In the last few years, though, various folks have kind of settled around call it a critique, call it a distinction, that we should not conflate social construct racial categories, things like African American, Black, Asian American, with statistical genetic statistical categories, things like very similar to a given reference panel. And this leads to, in the Hastings Center report on wrestling with social and behavior genetics, some of the authors of which are here, do not conflate human Thousand Genome Project populations with race. Similarly, in the National Academy's report a couple years ago on using population descriptors, do not conflate race, a socially constructed designation, with population genetic differences. Okay, so that's in the air. A natural question to ask. Now, another way of dealing with this is population geneticist Graham Coop, who said, not only don't use race, but don't use genetic ancestry. Instead, talk about genetic similarity, because we're interested in the kinds of genetic variants that are present in a population, and maybe in controlling for some of the differences for that too. I don't care whether Graham is white British in some kind of ancestral way. I care whether he's genetically similar to the Thousand Genome Project's GBR panel. So you can ask, okay, so how are geneticists actually talking about race, ancestry, genetic similarity? I grabbed a bunch of abstracts that are tied to GWAS catalog subscriptions or depositions. And I looked in their abstracts for different ways of talking about or operationalizing race. So this red line, the left is percent of papers of the 4,000 papers that had any of these terminology in them. The right is the number of papers. Many papers had more than one way of talking about population categories. The red is what I call quasi-racial terms. So that's anything from white or Caucasian, which are actually somewhat deprecated now, to things that we might recognize as OMB census categories, Hispanic, African American. The blue is that genetic ancestry term. So African ancestry, African genetic ancestry, both of those would be coded as blue. And then the yellow is a different basket of terms that tend to denote smaller populations. These might be national words, and it's often hard to tell whether this is referring to just we got these samples from China, or these are Han Chinese, just from the distant reading that I was doing. So I separated those out. And so you can say, well, maybe there is some slight decrease in how many of these papers are using these OMB statistical categories, starting maybe around 2018. There's a lag in how quickly the GWAS catalog indexes things, so I wouldn't trust any of these data after about 2023. There could be some selection effects there. So is this usage changing over time? Maybe it is, kind of. This is all US-funded work. If you're interested, we can see other funders at the end. But a lot of these terms are very US-centric. They're the US census category terms. These trends are also very sensitive to how I choose to code these data. And also, it's about word frequency. So it's not actually picking up variations in what people mean when they say African ancestry. Are they talking about a pseudo-racial category? Are they actually using that as a statistical genetic category? And I guess the other thing is only one paper that I found used this Coop genetic similarity framing. So that doesn't seem to be adopted yet. So if folks are interested in me pursuing this more, I'd be interested in your feedback, maybe in collaboration. But as far as the qualitative work, I think what's more interesting is how geneticists are drawing a distinction between these two different ways of talking about race versus ancestry. So again, and these are from trade books and textbooks, but I also see this in informal conversations at conferences and interviews. Melinda Mills and colleagues' 2020 textbook says, okay, genetic alleles, quote, have nothing to do with the social category of race. Dalton Conley's book last year takes a slightly different approach. He says, I can do social genomics within a group, but if I'm doing something about between group comparisons, between races, between genders, I still need sociology for that. Daphne Marchenko and Sam Trejo's book last year, thank you, says that unlike racial categories, everyone's place on the genetic family tree is not socially constructed. So they're kind of making the other intervention, saying this is not a social construct, this ancestry thing. So I think this is great content-wise. Like, I agree with all of these statements more or less. But it's not just content that I think this is worth analyzing this around. It's interesting analyzing what it is doing socially. And I think what this is doing is two things. One, it's signaling that social genomics is not trying to replicate some of the what is regarded as past mistakes around geneticizing racial categories. And it's also doing what sociologists of science call boundary work. It is delineating which methods geneticists think it's okay to use to address different kinds of population categories. It's delineating what kinds of variants GWAS is allowed to address, and it's also delineating science itself, which terms, practices, and people are in bounds in science and which are out of bounds. It's also in reaction to a more radical critique that I'll call the external critique that's coming often from sociologists of science. All of these folks are sociologists. Joan Fujimura and Ramya Rajagopalan, I recommend everyone read their work. They do some really interesting work on how the categories of race get kind of built into things like reference panels. But then you also have sociologists like Steve Sturdy, who does a similar kind of history of the population concept. But then at the end of his paper, will say something like attributions of ancestry are not a necessary step in large-scale genome-wide association studies. Or Rena Bless, who says that there's no reason at all to label genomic information with OMB data. So these are different prescriptions for what to do. Are we just kind of being careful and looking at the history, or are we excluding any information about race at all? Again, I think a lot of the empirical work here is very careful, but this is also doing some boundary work. This is also asserting that qualitative, inductive, and humanistic researchers like me ought to have some jurisdiction over what it is we mean when we're talking about analytical categories. So I'm a little biased here in saying that I think this work is worthwhile, but I do. But I'm not interested in telling you what you should mean when you say social construct, because I think people will continue to use the term social construct for both of these different social functions. What I want to note is that what I try to tell my colleagues is that there are reasons that people continue to use these, especially these genetic ancestry categories, because it's important not only to kind of parcel out variation, control variation when you're running a study empirically, but understanding variation is also important for selecting which populations you're going to be recruiting from. So the GWAS review pipeline that I pulled from, Melinda Mills and Chris Rahal set up the pipeline for pulling the GWAS catalog data, and that was all in the name of identifying that a lot of GWAS have been run in European populations and not a lot in other populations, which I think is a worthwhile thing to do and can't be done if you're totally agnostic about where these ancestry categories are. And I think it's really interesting that especially users of this technology of population sorting within social genomics, like Dalton, like Melinda Mills, like Sam Trejo, have been taking an active and intentional role in trying to shape what it means in saying that race is a social construct. I'm going to skip that. So rather than kind of arguing over what it means that race is a social construct, I think it's worth pulling from the philosopher of science Ian Hacking's notions of humankinds. Hacking says that humankinds are not a different kind of things than natural kinds. They're a subset of natural kinds, but they're interesting because instead of being indifferent, instead of not caring whether, if you're an HIV virus, you don't care whether you're called an HIV virus. But if you're diagnosed with autism, then you are going to not only change how you act in the world, but you're going to maybe take action to change what the definition of autism is. And the same is true not only of racial categories, but also of genetic ancestry markers. So Aaron Panofsky and Joan Donovan have this really interesting paper on how folks on white supremacist forums react to finding that they have non-European ancestry. And they're doing a lot of interpretive work to try to change what it means to have these ancestry informative markers. And the last thing I'll say is that technologies enable these looping effects to happen at different timescales and through different mechanisms. So the old racial category, that worked on the basis of feedback around phenotype and families. Now we have molecular genetics that's allowing people to set up new biosocial identities around genetic disease or genetic race. And I think that new technologies like polygenic screening and maybe CRISPR are going to set up new kinds of interactive kinds. What does it mean to be told that you have been selected on the basis of your genetic propensity for XYZ? And I think that's an open question that would be generative to consider, and that might be a more productive suggestion than just, oh, don't say social construct. So thank you.
Yeah, so I was thinking about that figure you had where you showed how the terms that people are using change over time. And I wondered to what degree that's being driven also just by different data sets are being used over time. Like, how would this look if you were to like include a data set fixed value? Like, do people talk about the UK Biobank data differently now than they did 10 years ago?
That is a really great question. I don't know. I thought about like all sorts of different ways that I could portion this out. Like you could try to fix the, correct for whether we're talking about European ancestry or African ancestry over time, because people will use different kinds of terms for each of those. You could fix it, fix the funder proportions. So yeah, there's a lot of different ways to parcel it out, but I think that's a really interesting potential one to do. And you do see, I think it's around 2018 that UKB really picks up. And those are going to be using, the terms that the UK chooses. And that might be why you see a decline in the US statistical categories. Yeah. Yeah. I didn't see that in many of the abstracts when I was hand looking at them. But that's, they might just say European. Thanks.
Can you say more, Bennett, when you talk to your colleagues back towards the humanities and you bring up the statistical considerations that you hear in this conference, is there much give and take after you bring that up?
So I think that what that gets read as among my humanist colleagues is that this is a descriptive explanation for why race and race-like terms, which they consider to include European genetic ancestry, African genetic ancestry. It is a description for why that terminology continues to exist in the sciences. Many of my colleagues are more concerned less about the scientific work than about how that goes and gets interpreted in the world. That's the Panofsky and Donovan paper. And so that's part of what's motivating the suggestion of, don't use these words at all, because that's what's being picked up in the public. I think that scientists should be careful about how they communicate. That's part of why I like the genetic similarity phrasing. But I don't think that scientists should not choose to use a concept just because it might at some point be misinterpreted. So I think the real work is in figuring out how to construct concepts and constructs and tools that are both useful, but then not too useful for for other purposes, which is that's an ongoing project that I know a lot of people are thinking very hard about. But yeah, I think that's what motivates this kind of intervention and saying, well, okay, don't even say European ancestry. Okay, thanks so much.
We see yeah, that looks like me. Is there a clicker somewhere? Over here. Does it move? It moves. Great. Okay. Hi, everyone. I'm Patrick Turley. I'm talking about something today that's very different than the type of work that I normally do. So apologies if it's a little scattered. So I want to talk about basically scientific efficiency of data sets and barriers to entry to the data sets. So why there are some certain data sets that tend to be used a lot more than others in social science genetics specifically. Just as a bit of a disclosure, part of the reason for me doing this project was so that I could experiment using AI tools in my research workflow. And so like almost all of this project was, at least the initial stages of it was done in using AI tools. So all of this code that I wrote to scrape the web, to process the data, to create figures, that was all done in Claude Code. I used ChatGPT then to review my code and the data. I went through and I spot checked the code and the data and things like, I did to the great can. So I take responsibility for everything that's here, but just wanted to let you know that a lot of this was done with AI and is also kind of preliminary. So, don't take me too seriously. Okay, so what motivated this study, other than the fact that I just wanted to play with new tools, is that the genotypic data sets that we use generally are funded with public funds. And so you'd think that funders would be interested in creating resources that are very valuable to society as a whole. However, if you look at these data sets, some are used a lot more often than others. And so I wanted to create this measure of scientific efficiency. And so the idea is, how much output is created by a data set given the size of that data set. And so when I say output, I'm going to be looking at three particular measures. I'm going to look at the number of genetics publications that use the data set. I'm going to look at the citations of those publications, and then I'm also going to use a term that's called the relative citation ratio, and it's just the rescaled citation numbers that accounts for the fact that certain disciplines and certain journals just get more citations than others, just because like medical journals just just the nature of medical research, there's more papers written, they cite more stuff, and so they just tend to have more citations relative to maybe like econ papers where there's fewer. And so it does kind of a rescaling to account for the fact that in certain field citations are maybe worth more than others. And then I'm going to scale all of these by the number of genotyped samples in the data set. And so if there's a big data set, but only like half of it's genotyped, I'm just going to look at the number of genotyped individuals, because I'm interested in the more narrow question of how efficient is the genetic data in these data sets. So kind of the two high-level questions that I want to be thinking about is first just a descriptive question, like how much variation is there in scientific efficiency across cohorts? Because I think initially that's also just, I think a nice thing to know is that are there data sets that are just way more efficient than others, and by how much? And then I also wanted to get some measure of like what's predictive of scientific efficiency. I would like my predictors to be related to barriers to entry, but something that I can measure objectively. And so I'm going to talk through what I use to do that when I get there. I'm interested in getting people's feedback to think about like, is there a better way that I could construct this? How interpretable are the measures that I'm going to use? So we'll talk about that in just a minute. Okay, so how did I collect the data? So first thing I did is I just scraped all the papers I could from PubMed and Europe PMC in approximately the last 3 years. I scraped them looking in PubMed. I would look at the cohort names. Look for the cohort names in the title and abstract. In Europe PMC, I was able to you can scrape the acknowledgement section. So I was also able to look at if that data set is mentioned in the acknowledgements. And so I got a great big set of papers that mentions each cohort individually. And then I searched the titles of these papers to see if it's pretty easy to categorize the paper as a genetics paper or not. And so my script would put things either like if it talks about genetics, then like it's definitely genetics. If it like talks about like epidemiological stuff that's clearly not genetics, it would say that's definitely not a genetic study. But then like about half of the papers it would say was ambiguous just by looking at the titles alone. And so from there, I passed that data set into ChatGPT and I said, can you validate both the ones that are included and excluded, but then also categorize the ones that were ambiguous? And I think it did there's thousands of papers, so I haven't checked every single one. But when I looked through, like for the most part, I thought that it did a pretty good job. The things that I would have called a genetics paper or epigenetics paper, ChatGPT also called a genetic or epigenetics paper. So, again, there might be some imperfections. This is still preliminary work. I'd like to do a little bit more to validate things myself, but I think it's pretty reasonable. Here's just a list of the, I just try to come up with the cohorts that I could think of that are used in the research that I see. So these are the studies that I used here. There are probably a few that I should probably add that I saw some of you doing presentations and like Midas, I think someone used that's not in my study here, but this was just me thinking list. I didn't do anything systematic to pick these. These are ones that I see when I'm doing research myself or looking at research. Okay, so this is just first the question, how, what's the distribution of efficiency in publications per genetic sample across all these different data sets. I've just made like a kernel density function. We can see that spans from, like -4 in log 10. Notice that I'm in log units here. So -4 in log 10 to about -2. And so that means that like that's 2 orders of magnitude. And so, the papers that are on the -4 side are create 100 times less publications per sample than the ones on the other side. I've listed the data sets that are kind of the bottom 5 and the top 5. So we have like the Danish National Blood Cohort, I think is that one, 23andMe, the Mexico City prospective study, down on the other side. So these are ones that have very few publications per sample. And on the right, we have like Twin Life, we have Framingham Heart Study, UK Biobank, ALSPAC, Future of Families. And so these are ones that tend to have a lot of publications given how large they are. So then if we wanted to look at, I also measured citations, and I've just plotted them against each other here to show that, like, yeah, there is some variation. There are some public cohorts that have a lot of citations relative to their publications and less, but it's quite highly correlated in general. And if we look at the relative citation ratio, still it's high, it might be even more highly correlated as well. But yeah, so all of these are sort of measures of output of these cohorts given their sample size. Okay, so now I'm going to talk about the measures of like barriers to access that I've tried to construct. So the first one I call the top 3 author concentration. So what I did is I looked at, for each cohort, I identified 3 authors who all of their papers together cover the largest fraction of papers that use that data set. And so, this is supposed to represent, like, if there are just a small number of researchers that are on every single paper that use that data set, wow, okay, then this number would be high, whereas if it's a cohort where, like everyone's publishing that data set, we have a very small number. And so this also is a high range. So UK Biobank, this number is 2.8%, but like Dunedin, the Minnesota Twin Family Research Center, Mexico City, like those 100% of papers have the same 3 papers on them in the past 3 years. And so if I plot the authorship concentration on the bottom here against the publications per N, there seems to be kind of a slight downward relationship. And so studies that have a very high concentration, the same people on every papers, tend to be less like scientifically efficient than ones that lots of people are using. And we have the same pattern when we look at citations or when we look at the relative citation ratio. The Usher method, this one is more preliminary. I asked ChatGPT who are the members who are like governance authors for different data sets. So these people are like the founding investigators, the people who are on the governance committees, and I just got a list and I said, what fraction of papers include members of the governance committees for each cohort? And so it's another measure of like, if this is really high, it might mean that, it's necessary for you to get inside help to publish papers in this area. So, it's not perfect, but we again have this big range with UK Biobank being have a very small fraction, and like Dunedin, 100% of papers from Dunedin have at least one person from the governance committee. And the relationship here is similar, but more shallow. You can see the relationship's not quite as strong. Now, one thing you may be thinking about is like, well, there's lots of confounds here, where this maybe is not representing barriers to entry. And those are the things that the main 3 that I thought of that are easy to access are just sample size, the age of the study, and the funding source of the study. So you might imagine that small cohorts, like people may not be as willing to pay the cost of like applying for the data and submitting the application if there's only like 1,000 people in the cohort. And so, small cohorts may have that. They may have more specialized phenotypes that are of interest to a smaller group of researchers. And so that would both change the scientific efficiency and the authorship concentration in ways that don't really have to do with barriers to entry exactly. If you're a newer cohort, it might just be that fewer people have like learned about you and started using your data. They might not have worked out the kinks in data access. If you're a publicly funded data source, then like maybe your priorities are different than if you're like 23andMe, who like doesn't probably care much about scientific efficiency from a like, publication standpoint. And so I'm just going to finally show a few estimates where I residualize out these controls and see what happens to these relationships when I residualize these out. And so just to give a sense, this is just showing, on this side I have. So I'm just going to show for the sample size here, and these are the efficiency measures on the left. And you can see that larger cohorts tend to have fewer publications per sample, and like larger cohorts tend to have a smaller concentration. So like, UK Biobank, there's lots of people are using that data. And so, because of these relationships, you could imagine controlling for them would affect what we see. And so to see if it does affect, so this is the same figure I showed you before, On the x-axis, we have the author top 3 concentration. On the y-axis, we have publications per sample. When we control for the things that I told you about, we still see this strong, in fact, this becomes a much stronger relationship. So once you account for sample size, this authorship concentration thing becomes actually even more important relative to how efficient the data are. So we could do this as a regression. If I just wanted to regress the authorship concentration on our 3 scientific efficiency measures, controlling for the things I told you about, we see just these really strong negative relationships for all 3 efficiency measures. If we look at governance fraction, we still see something that's like, medium strong for publications, but nothing significant for citations or the relative citation ratio. And so, so what I think the takeaways are, I don't necessarily have like policy recommendations. And we do see that, whatever the top 3 author fraction represents seems to be really important for how efficient a data set is, how valuable it is to like the people who are funding these data sets. Governance fraction seems to matter maybe a little bit, but not quite as much. But like we can't really interpret these causally. Like it's not that by just increasing the author concentration that is necessarily going to fix things. But I think that as we think about these, we all work with these data sets. And as we think about like the attributes of some of these data sets, like I think we maybe have a sense of like, well, what is it about the Million Veterans Project that means very few people work with that data? And so, in fact, so I have this as an example, I told you not to treat things causally, but I'm going to do it anyways. I'm going to move in that direction at least. So if we wanted to compare the UK Biobank to the Million Veterans Project, both of these data sets were genotyped in 2015. They have really similar sample sizes. However, they have a very different authorship concentration. UK Biobank's 2%, whereas the Million Veterans Project, almost 30% of papers have the same 3 authors on them for the Million Veterans Project. And so if we just think about these regression, like, this figure I have here, Million Veterans Project's right here. And let's say that they were able to change their access policies in such a way that they were able to push their authorship concentration to be similar to that of UK Biobank. So we just move it along the line here. What that would amount to is increasing the number of publications that they've had from 300 in the last 3 years to 430 in the last 3 years. So it's like something about the access procedures, something about the policies that are in place, and maybe the limit. Maybe these policies aren't the fault of the data set. It might be just the policy environment of how the data were collected and things. I don't want to like assign blame or anything, but something about the Million Veterans Project is costing society 130 papers a year. That it'd be nice if we could have those papers. And so like I think if there is any sort of takeaway, I would think if you're someone who works at these data sets and setting policies, then it's worth thinking about like, and you find that you're in a kind of a low efficiency data set. Like I think it's worth thinking about like why, like what could we do to increase access to kind of push ourselves more towards a UK Biobank level of just democratization, or if if you're a funder for such a data set, maybe it's worth pushing these data sets to think about what they could do to improve access. Or if you're a viewer for a grant for one of these data sets, it might be that like if they can't do it, that's good to know why. I think it's worth thinking about why, and I think that these data sets should be able to justify, what makes them different, what makes it harder, because there seems to be a large cost in terms of just scientific value of these data sets that exist. So that's that. Thanks, everyone.
That's very cool, Patrick. Very interesting. So you're talking about access procedures. So have you thought about trying to quantify that? Like, right, there's different data sets. Like, how do you sort of quantify the different dimensions of how hard it is to access and how costly those are in terms of the efficiency? And
yeah, I love that idea. I when I was doing this paper, I was trying to think of ways to quantify barriers in sort of an objective way that's short of doing like an audit study, because I don't have the time or money to do an audit study. So like if there was an easy way to collect data like that, like how long it takes from the time you apply to getting the data, or it just seems like that information is not generally easily available in an objective to measure way. But I agree that would be great.
And I don't know, I think sort of just starting from whatever descriptions they have of how to access the data and all the steps involved, and sort of that may give you sort of ideas of how. So that's where I kind of would start.
I mean, some of the problems is that for some of these data sets, the steps just aren't even easily available.
Yeah, so that's in itself.
I guess yeah. But I don't know how to turn that into a number that I can stick in a regression.
Yeah, maybe I that's very interesting, but maybe I missed in the very beginning. But I'm just wondering, is it possible you can just collecting data only based on the data name, like the data set name, rather than based on topics? Because I'm just thinking about, like, if we are looking at different kind of topics, when we think about the barrier, there could be two different things. One is like more general, like the access fraction, like people need to put a lot of effort to access the data. But on top of that, there could also knowledge barrier, right? So if the data is very specialized, then some people may know the data pretty well, and other people don't really want to put a lot of effort on that.
Yeah, and I tried to sort of nod to that before. I mean, I think that is something, one of the things that may drive it is if a data set is very specialized and it's like messy electronic health records that are just not worth the trouble of trying to learn, then like that might be one of the reasons why there's a high authorship concentration. So like I know, and I would classify that as a barrier. Like if making the data available in a format that is easy for people to read and easy for people to analyze allows you to push you into this high efficiency setting, then that would also be great to know.
Right. I mean, but one variation could come in from, like, I'm a little bit more familiar with UK Biobank, and besides the genetic part, it also have like much more other variables they are using, right? So even people are accessing to the same data set, they are looking for different things. So there you may able to differentiate whether it's really about accessibility, like the general friction, or it's more about like the specialized knowledge friction there.
Knowledge about the phenotypes in it, or knowledge about the access?
Knowledge about the phenotype. Like
that's true. Yeah. And so data sets that like there are certain data sets that have a very narrow focus in what they're trying to study, and so that was maybe what but those don't tend to be large data sets. You don't collect 1 million people so you can study breakfast cereal.
Okay, thank you.
Thanks, Patrick. This is really cool. So two questions. One on kind of the discipline to discipline, field to field differences. There's definitely differences in citation practices, and I think citation ratio is a good way of looking at that. There's also differences in what a paper-worthy study is in a given field, and I don't know offhand how to account for that. But did you give any thought to that?
Yeah, I mean, I think that looking at citations instead of publications was like meant to step in that direction. Like you could imagine that like there's 1 million papers that no one reads that come out of a particular data set, and so to the degree that we think that citations are a measure of how valuable the field thinks the paper is, like it tries to get at, and the RCR was meant to even take that a step forward. Like I was looking at one of the most like efficient data sets was the Framingham Heart study. If you looked at but those are primarily medical papers, I think, that come out of that study, which is why I was like, I need to have something that accounts for the fact that these like highly cited medical papers make up the vast majority of the papers coming out of that study. So what I did was an attempt to address that. I don't think it's perfect.
Yeah, and then the other thing is qualitatively, I've heard people concerned about like UKB switching from downloads to like a cloud-based access model. Is there any way that you could do a when do data sets make the switch, and
I did.
Does the
so before I
efficiency
started
decline?
this one, I was doing exactly that. I did like a time series of the number of preprints that are coming out before and after they switched, and it looks like there's a small dip in the year the UK Biobank switched to the cloud, but I don't think the dip it's not very robust, and it's small relative to the total number of publications coming out. I thought I was going to see like a huge, like a crater, and you don't see a crater in the number of preprints coming out that use UK Biobank data when they switch to the wrap.
Thanks, Patrick. That was awesome. I really enjoyed it. I had a question about whether you thought about the way these studies were funded and how, like, what type of NIH mechanism, and because my understanding is like with HRS, they have a U and they have to get the data out right away. Whereas if it's funded with an R01, you can hoard it for a while. You do have to get it out eventually. But my understanding is, and of course, researchers have incentives to do that because they've just spent years collecting these data. They got a big R01 for it. They're going to try to get as many publications out. And then there's also this lag time in when things end up in a repository, like with NIAGADS. So even if someone who wrote an R01 has the best intentions of getting something into NIAGADS as soon as possible, my understanding is sometimes it can take up to like 2 years.
Yeah.
And meantime, you've got all that data sitting on your server so you can keep publishing papers.
Mm-hmm.
So I wonder if you've thought about, and then of course the European situation is very different. So I wonder if you're talking about type of funding mecanism.
Yeah, that's a good point. I mean, I guess I did try to differentiate, at least, government funding versus like philanthropic funding. Like you color coded this figure. You can, and so I didn't think about like U versus R,
yeah, like
which is interesting.
Heterogeneity. Yeah.
Yeah.
That my understanding is that makes a big difference in.
Yeah. But you do see that like, public funds go all the way, across. There's a huge variety both in the author concentration and also the scientific, publication per sample, even among government funding. But I think splitting maybe more finely could be. We don't have that many data sets as part of the problem too. So you can't split. I have 36 data points.
But it'd be cool to show that to the NIH to be like, hey, look, like this is something that's holding us back from doing better science.
Mm-hmm.
It's these little, kind of institutional and.
Yeah.
Yeah.
Thank you.
Okay, good morning. So glad to present my work here. We work on something related to all of us, and this is a joint work with my colleague Evelina Akimova at Purdue Sociology. So the project starts by looking at the distributions of the birth year data in the all of us. So all of us is a biobank in the United States, and in the left figure, we plot the birth year distributions across the different genetic ancestry group. The blue is European, the red is African Americans, and the green is Hispanic Latinos, and the right figure is overall U.S. birth rate. And you can see there's a increase of the birth rate after the Great Depressions and to the middle of the 1950s, 1960s. So this is a period of the post-World II baby boom, and then it declined in the 1960s, and then stays relatively stable, and is somehow also roughly consistent with the trends of the growth of the European populations in the all of us research data. The specific research questions we are asking is, given there's a long span period of the birth year in the all of us, can we identify the genetic variants associated with the birth year? So birth year is typically not considered as a biological trait, but it has some implications of such identified variants because it may show some allele frequency change across different birth cohorts. And historically, previous research when they're trying to identify the change of allele frequencies across the birth year, they often focus on comparing with ancient DNA with modern DNA and their interpretations about the natural selections. Although the environment nowadays is pretty much different with the ancient period, but maybe there's some of the socioeconomic factors or the policies or other culture change that may result in the allele frequency change. So the approach we're doing is we simply treat the birth year as a continuous trait, and we perform a GWAS of the birth year on the first is the intercept, and the G is the genotypes, and W is the covariates. We adjust for top 10 PCs about the population stratifications as well as 6 at birth. So the data we are using is all of us 8, version 8 ACAF whole genome sequencing data, and we select the common variants, performed a rough Hardy-Weinberger equilibrium filtering for the European populations, and we remove the related individuals, and we perform the analysis separately for the European, African Americans, and Hispanic Latinos, and genetic ancestry is provided by the all of us. So I will first show the results for the African Americans and Hispanic Latinos. We find roughly 1 or 2 genes that is significant after multiple testing corrections. So these genes are functions. Some are related to the cardiovasculars, so mostly are health-related genes. But this presentation, I really want to focus on the European results because we got some of the interesting findings. The most significant one is on chromosome 19, the ApoE. So this is closely related to the Alzheimer's disease. And besides, we also got some of the other significant genes, and most of them, they are related to the neurology. We got the tau proteins, MAPT, and KCNB2, and ZBTB18. I think they are all some channel proteins. And we also find a significant genes that is estrogen receptor, so it is related to the fertility. And the overall heritability is about 0.04. And we also did a functional enrichment analysis and find that it is enriched in the brain. Because of the availability of many large sample European GWAS summer statistics, the next we focus on the European populations for the downstream analysis. So these are two examples of the genetic variants we identified with in the previous plot. And here we basically show the allele frequencies, how they change across birth cohort, starting from the first being, which is 19 to 1929, and the last one is close to 2009. So the first one is our ApoE epsilon 4 allele. So this is basically reflecting the viability selection due to Alzheimer's and dementia. And you can see starting in the early cohort, they carry significantly, the allele frequencies is less than those who are born in the later cohort. And people carrying ApoE epsilon 4 allele are more likely to have Alzheimer's disease. And the right one is on the estrogen receptor. So you can see this kind of the change of the increase of allele frequency starting from the 1939 to about 1960s. And then they stay relatively stable. About the replication of the findings, so none of them can be replicated in the UK Biobank, which has a different birth year distributions. Also, the social environment is a little bit different. But ApoE is first discovered by a previous study using a genetic epidemiology research, another biobank in US, and they find that ApoE really has some of this allele frequency change. But for other genetic variants, we cannot replicate results. So the next, we're trying to see what kind of the traits are correlated with the genetic variants we identified with allele frequency change. So we basically performed a genetic correlation analysis using our birth year GWAS summer statistics with a large number of the GWAS summer statistics from other traits. So here, the positive genetic correlation means the alleles that are more common in the later birth cohort, they are associated with increased value or risk of the other traits, and the negative genetic correlations means it's associated with a decreased value. So because most of the genes, they are associated with neurology, so we first start with neurological traits from the PGC consortiums. And we try a bunch of 7 or 8 traits, and we found that 4 of them, they are significant after multiple test correction. We find that the positive genetic correlations with ADHD, major depression disorders, insomnia, and substance usage disorders. And the ADHD had the highest genetic correlation, it's about 0.4. And we also tried a bunch of the reproductive traits in UK Biobank, and we see that there's positive genetic correlations with, for example, number of children born, and the negative genetic correlations with age at first sex and age at first birth. So it basically reflects a positive genetic correlation with fertility. And with the social behavioral traits, positive genetic correlation with smoking, alcohol taking frequency, and negative genetic correlation with their income, and as well as whether they take the disability allowance. So Then the last part is we use the polygenetic score to examine the same questions. And what we do is we construct the polygenetic score using the external summary statistics. And then we try to identify the individuals in the top 5% based on the PRS. Then we look at the distributions of these individuals across the birth cohort. Then under the null hypothesis, this proportion should remain approximately constant at 5% across the birth cohort if there's no birth cohort effects difference. So the first one is Alzheimer. You can see those in the 19 to 1929. So there are less there's less proportions on identified as a top risk for based on PRS, and similarly this patterns holds for ADHD. And also for the major depression, but as a negative control sample for the autism, you don't see that the significant deviance from 5%. And for the reproductions, this one is more clearly effects where you show that those identified as a top PRS percentile, there's more people born earlier have like bigger age at the first live birth and compared to the later cohort, and the same for the age of first sex. And this is for the age completed educations, where you can see there's a trend where there's more people born before the 1950s. They kind of have a higher at higher proportions in the identified based on the PRS. So our discussion is we first have identified the genetic variants that shows allele frequency change in all of us, and their functions is more related to the neurological functions and also the reproductions. And this pattern is consistent with the possibility of the natural selections acting on the reproduction traits, although there may be other possibilities, such as participation bias and the demographic migrations, which we currently cannot account in our analysis. And the last one is the allele frequency change of the variants associated with education attainment may show decline across the birth cohort, but we know that the college attendance has increased over time. So this basically shows that genetic trends and social trends can move in the opposite directions. And in this case, it probably means the social policies has much impact on their education than the genetics. So as this acknowledgement, we thank the participants from all of us and UK Biobank, and this research is supported by Analytics Fellowship. And thank you and welcome any questions.
Thank you. So I do understand that in the sort of discussion slide, you mentioned the sort of selection, the participation bias, but it wasn't until the end that you mentioned that, right? And it was framed a lot as change in frequency, allele frequency, but it seems a bigger problem than it may have seemed, right? Like the ApoE, it could be just mortality, right? It could be that those people are dying. So, and we know that those data sets.
Great. So I'm really glad that we've had almost a day and a half of just really wonderful conversations in science, and we're just so pleased that Shai could join us. He's had a difficult travel scheduling issues, but we're so glad he came in person. We have a lot of interest, I know, among the crowd here in this topic. I'll just do a very short introduction because he's got many papers and many domains of expertise in statistical genetics and in population genetics, but more recently, he's really been on the cutting edge of both analyzing and thinking about ethical and statistical issues around human embryo selection. So, he'd really like this to be a lot of Q&A discussion during the talk. So he'll even so be thinking about that as the slides go through and as the discussion progresses. Think about what questions you have during the talk. There'll be some times that he's going to stop during the talk and ask for communication among you, so have that ready. Be warned. So let's join me in welcoming Shai for our second keynote.
Good afternoon, and thank you so much for inviting me. It's been a great conference. Yes, I'll talk about screening human embryos with polygenic scores. The goal is to give you an overview of the current state of the literature to make sure you're informed regarding what is known or unknown about embryo screening. And I'll try to make it interactive. I already had some very good discussions in this conference. It would be great to have more during my talk. Okay, so 1 second. Okay, so let's start with some background, kind of technical background about embryo screening. Technically, it's called pre-implantation genetic testing, or PGT. Sometimes it goes by the old name PGD for diagnosis. And the way it works is that we have the embryo generated by in vitro fertilization, and the embryo grows in the lab for a few days. This is day 5 embryo. It's called the blastocyst stage. And for genetic testing, it is possible to take a few cells from the outer shell of the embryo. This part is called the trophectoderm. It develops into the placenta, so we're not actually removing cells from the embryo proper. It does not harm the embryo. And then DNA can be extracted, amplified, and then tested. And traditionally, labs used to test only a specific type of variant, or even one specific variant for each couple, depending on their indication, either so-called PGT-M for monogenic. So, for example, if parents are carriers for cystic fibrosis recessive variants, they would like to make sure the child is not affected, is not homozygous. So they would test for this specific variant, or very commonly structural variants, or aneuploidy, which is a missing or extra copy of a chromosome, which is common with advanced maternal age. And it's useful to screen the embryos so they are not will not be transferred, and because usually they do not lead to pregnancy. But over the past decade or so, now we have next generation sequencing technologies and microarray technologies, and labs found that increasingly it is easier, more affordable, simpler to just use genome-wide technologies of various types, even if they're just looking for a single variant. Because instead of developing specific assay, a special tailored assay for each family, now they can just test all the families in the same way, and sequencing is cheap enough that it's just much easier. So many labs now have this technology in routine use, and they're just generating whole genome data for all embryos all the time. And but they're not looking at what's in the data. And the question that arose in the past few years is, should clinics, IVF clinics, or genetic testing labs, should they start looking into also polygenic traits and diseases? So this is called polygenic embryo screening, PS. Some authors call it PGT-P, P for polygenic. We try to focus on, we try to call it PS because we don't want to imply it's as diagnostic as the other types of PGT. And the way it would work is that, oops, sorry. Okay. Wait 1 second. Okay, and the way it will work is that we have the couple undergoing IVF treatment. They have their embryos. We have genetic testing of the embryos, and then we compute polygenic scores for one or more disease or trait, and then we rank the embryos based on their risk. So here in this case, embryo 1 has the lower risk for both conditions, so we would prioritize it, and we will deprioritize the other embryos. But it's also important to mention that polygenic embryo screening can actually take many forms. It's not just one type of screen. It can be implemented in multiple ways. For example, are these patients, are they already undergoing IVF or infertility or not? Are they screening for one disease or multiple diseases? Do they already have a history of one of those conditions? Are they also looking at traits? What are they going to do with those low priority embryos? Are they going to discard them or maybe use them for the next child? Or maybe use them if that embryo is not born for some reason, like the prioritized embryo, and so on. So there are many ways to implement it. And diving more deeply into the nuances of what happens with like different types of implementation of PS is one thing that we try to do in the research. Okay, so where can one get PS? So in the United States, it's legal. PGT is not regulated in the United States at all, so parents can select for sex, for eye color, for skin color, whatever they want. There is no limitation whatsoever. Right now, there are 4 companies offering polygenic embryo screening. It's expensive. Obviously, we have to sequence the embryos if you want to offer polygenic embryo screening. So the minimal cost is around $5,000, just the cost of sequencing. But some companies, for example, Herosite, they charge $50,000 for the entire procedure. What are they testing for? Around 10 to 20 conditions in each of the company. Some cancers, cardiovascular conditions, the diabetes, gastrointestinal, some neurological conditions, kind of a standard list of conditions. But some labs, Nucleus and Herosite, also test for traits, and Herosite, for Herosite, it's intelligence. This is specifically what they are. This is the only trait they're looking at. How many were tested so far? How many embryos were couples used it? How many babies were born? It's very difficult to tell. I would say my estimate is between high hundreds and low thousands. Companies would not share the numbers, or they just lie, unfortunately. So it's difficult to find reliable numbers, but that's my, at least, numbers that I can be confident with. And recently, it attracted a lot of attention from the media, particularly with Nucleus and Herosite, because they screen for traits and intelligence, and because their main clients are coming from mostly the richest people of Silicon Valley. People are sometimes obsessed about like the lives of those people from Silicon Valley, because sometimes they also set a trend, and people are worried about it. Okay, what about other countries? So it's not. So in most countries, it's illegal. In some countries, there are clinics that work with the companies in the United States and just send samples to the United States. But it's also important to realize that it's also relevant to some other countries. For example, in the UK, it is prohibited by law, but patients can take the data that was generated by their local genetic testing labs. They can just request the data. And they send the data to the United States for interpretation, and then they select embryos based on the interpretation, based on the polygenic diseases or traits. So it's really everyone's maybe problem or opportunity, depending on how you see it. So what I will do in the rest of the talk, I will try to cover the following angles of PES. First, talk about ethical and social concerns regarding embryo screening. Then talk very briefly about the stakeholder attitudes. Then most of the talk will be dedicated to statistical considerations, like what are the actual gains that can be made with embryo screening, what are the medical benefits. And then if we have time in the end, I'll also talk about clinical considerations. And soon I'll give time for some questions, but I would like to first cover ethical considerations. So what I will do in the next slide, I will show the ethical concerns that were raised by various authors regarding embryo screening. And that is not to say that all the ethical concerns are equally worrying, or these arguments are equally strong. Some are stronger, some are weaker. I will also present counter arguments, but I just want to give like the full picture of what people are worried about. So obviously the main problem that people are worried about is eugenics. Every attempt to control reproduction in the way that will make the humanity change the, make humanity better or change the gene pool of humanity can be called eugenics, and people are worried about it. The problem with eugenics, it's not really well defined, and I'm sure everyone here in this audience struggles with those questions. What exactly is eugenics? What exactly is wrong with eugenics? And of course, we don't want to somehow go back to the atrocities of the 20th centuries. But it does not look like this is going there. I mean, we're talking about something that's initiated by the parents. There is no coercion. Nothing is compulsory. So it's not really a problem in that regard. But maybe when people say they're worried about eugenics, they mean more nuanced problems like this slippery slope toward selection for traits or optimization, which actually happened. As I just mentioned, and also questions of reproductive norms and parent-child relationships. Are we going to reproduce in a different way, in the future? How is it going to make us feel about, the way we feel about our children, and so on? These questions, make a lot of people feel uncomfortable. And maybe this is they can fall under the issue of eugenics. And then there are also many other problems. One issue for some people, there is problem to discard the embryos because they see embryos as persons. So of course, every PGT is a problem. And then there is stigmatization or discrimination against people affected with the conditions that are screened or the traits that are screened. Regardless of whether a certain person was screened as an embryo or not. And another problem, because it's expensive, is unequal access to the technology. It will work better in people of European ancestry, so the benefits are not equal. Another problem, which I think is not discussed enough, even among scientists, and of course also among the public, is distraction from non-genetic causes of diseases. Because we spend a lot of energy talking about ways for to screen the genes of embryos, and all these debates that we are having about this technology. But in the end of the day, a lot of conditions are much more environmental than genetic, and we could have just spent all those efforts on eliminating or mitigating environmental risk factors. So that I think is an important consideration. Some complaints about shifting responsibility for disease preventions to the parents instead of treating people with the condition as a society. Ignoring the lived experience of affected people. So if you ask people with, let's say, diabetes or Crohn's disease, if they're happy with being alive, most of them are happy that they are alive. They would not have wanted to be screened or eliminated as embryos. They're happy that they were not screened. So maybe this is a consideration. Another consideration is the commercialization or medicalization of reproduction, which most of the time does not need medical treatment. And also, this will be familiar to some of you here. Some people raise concern about harm to participants in genomic studies who did not consent for their data to be used downstream for embryo screening. But there are also some convincing, I think, partly convincing counter arguments why a lot of these concerns are not so worrying. So one main point is summarized as choice over chance. I mean, this is by one of the companies, and the idea is that we have those embryos because usually IVF generates more than one embryo. So we need to select one of them. So right now it's almost at random. The selection is being done based on morphology, and there's no very strong evidence for that this selection is effective or important in any way. And it's and then why not use the information that we have for more informed selection? No coercion, as I mentioned. Stigmatization maybe is expected, but also will not necessarily happen because of screening. Not strong evidence for that. Maybe lowering the prevalence of some conditions will actually reduce stigmatization. An important argument is reproductive autonomy or patient rights. If patients want to have the data, if they want to screen their embryo, they should be able to have the opportunity to do that. They should receive the information. Eventually, it will benefit the future child to have maybe more favorable traits. or less disease burden, and parents can be stopped from investing in children, right? So we cannot tell parents, okay, don't send your child to a private school because there is inequality or some other concern. And maybe in a similar way, we cannot tell them not to screen their embryos. Some people talk about how this decision is going to be difficult, but we are expected to make difficult decisions throughout life. This should not be different. And then regarding equality, then most technologies start as expensive, only available to the richest, and then they become cheaper over time. Any questions so far or points to discuss? Yeah, please. It's also okay if you just have comments. It's fine. I mean, people have an opinion.
I think this is like a comment brainstorm. So you were mentioning something about benefits to the future child.
Yeah.
And when we think about some of the conditions that are more beneficial for people in their middle stage of life, so to say, right? And over this last days, we were discussing APOE a lot and Alzheimer's disease. So say you screen the embryo for APOE, and we're learning like this as well that APOE is actual protective, might be protective in the for the children at their early stage of life. So I'm just wondering, has anyone been thinking about it? Like what is actually protective for kids in the early stage of life? What we might be screening as a negative thing when we measure it mid-stage of life? Just, Yeah, so
I'll get to this question, not specifically regarding APOE, but question of pleiotropy. I'll get there when I talk about statistical considerations. Yeah, thank you. Yeah.
When you said IVF creates multiple plausible candidates, are they currently just randomly chosen, or are they chosen because
they're chosen
one is more likely to survive than the other?
Yeah, so the way clinics choose them is based on the embryo that they think, based on the morphology or the development trajectory, is most likely to lead to live birth. Usually based on like how many cells are in the embryo, like the structure of the embryo, whether all the parts of the embryo is developed properly. But it's very common that you have multiple embryos that they all look almost equally competent or viable.
Fair to say that the list of argument and counter arguments you have on these slides are not specific to PRS. So the same thing can apply to monogenic selection as well.
Yeah, I think I think that's right, but I mean, some points are specific to polygenic, for example, like environmental causes of disease, patient confusion, which I will get to when talking about clinical considerations. But yeah, a lot of these, I mean, unequal access is also consideration. I mean, some countries, PGT-M, for example, is funded by the government. So it's not like the parents have to worry about how much it costs. So yeah, but that's true that a lot of these considerations are common to PGT-M, and that's one argument of particularly the companies who offer this, is that PGT-M was also very controversial, like 30 years ago when it started, and it became even more controversial when they started offering it for not only for like very severe diseases with very high penetrance, for variants with very high penetrance, but also for variants of kind of penetrance less than 100%, like BRCA variants, for example, for breast cancer risk, which can increase risk by a lot, but they are not. But people are not guaranteed to have the disease. But right now it also falls under PGT-M. So the argument is that like the same way people became used to PGT-M, they will also get used to screening for polygenic conditions.
Yeah, the argument that lowering prevalence might reduce stigmatization. Is there a specific case or trait that there's a big one for that?
So that's what I saw that argument in a paper that came from one of the companies, and I thought it was well. I didn't dive deep into the sources, On the other, I also didn't see anyone citing sources for the argument that it would increase stigmatization. So I think this is one place where we need more empirical studies. A bit difficult to properly conduct it, but yeah, I mean, one problem with these arguments is that they are sometimes vague arguments and maybe moral arguments, but actually we can come up with data to, you know, for example, like shifting responsibility or destruction. Like, are we actually, I mean, so maybe we think that we are being distracted from other causes of disease, but maybe we ask people, let's say we implement PES, we give it to everyone. Are we going to invest less in eliminating like a, you know, environmental risk factor? Maybe not. Maybe one does not come at the expense of the other. So these are, you know, can be framed as concerns. Maybe not like very specific risks. Okay. Thank you. Okay. So now, yeah, and okay. So, you know, whether we like it or not, I mean, it's probably going to stay with us. It was highlighted recently by MIT Technology Review as one of the 10 technologies for this year. So it's probably here to stay, and we have to, you know, to think how to deal with this technology. Okay, so what do people think about it? So healthcare professionals overwhelmingly oppose the technology. Same for academics, from what I see informally, but particularly healthcare professionals like reproductive medicine specialists and genetic counselors, they are strongly against polygenic embryo screening. They're mostly skeptic about like whether it's good for anything. They think it will be difficult to understand, will confuse the patients. They're worried about all the ethical considerations, social considerations that I raised before. And this was shown in multiple studies, and also, you know, every time I talk to, you know, I give this or a similar talk to healthcare professionals, it's like, it's very, that's the sentiment. I mean, it's very clear. There was one study on PGT patients. They found it from Belgium. They found it not very useful, and they didn't want it because of their difficult personal experience so far. On the other end, the attitudes of patients, IVF patients, and the public is quite positive, which is interesting. It's intriguing also, and also it implies that there is a gap that we need to think, okay, what is the problem? Is it that healthcare professionals maybe do not understand what people want, or maybe the public does not understand all the limitations and possible harms? So the gap must be somehow closed. So again, multiple studies now support it. The one that highlights are from my group and colleagues. Yeah, so people, particularly for diseases, they approve it for something like 70% approve it for everyone. Some even approve it for traits, although of course much lower frequencies. People do have concerns. And we also did like an experiment in one study. We found that it's relatively easy to kind of trick people to be more or less concerned. That's a limitation of all those surveys. Like, you just show them all the problems before or after you ask the question. It changes quite a lot the levels of approval. So all these studies have to be taken with a grain of salt. But overall, the sentiment is positive. I'll tell you just a little bit about our study in Jerusalem, the analysis is ongoing now, so it's unpublished. We performed it at the Shaarei Tzedek Medical Center, which is a large hospital in Jerusalem. It's actually probably one of the largest PGT centers in the world, because we have a lot of very large volume of PGT in Israel because of many founder variants in Israel. So it's the lab head is Geona Terescu. My student Gilad Sachs, she actually went to the hospital, to the IVF and PGT clinics, and she recruited something like 400 people to the study. She gave them a survey, and the number of people that eventually agreed to participate, completed the survey and passed comprehension checks was around 270. And the results were quite similar to what we saw in previous studies in the United States. About 50 were strongly interested for themselves in polygenic embryo screening for diseases. And almost 80% if you also include moderately interested. In terms of approval for PES for diseases was very high. 84% approved, only 3% disapproved, but for traits, quite low, only a quarter. This is even lower than what we saw in the United States. And we even had enough data to find factors that are associated with high levels of approval or interest. For example, being older, slightly increased approval, being born in Israel, being politically conservative. I think older was, so Patrick also had a study a few years back, and I think he found the opposite direction of effect. It is to be determined, we need to think why we see opposite effect, and so on. We also see, but as was found in the Belgium study, we see that being in the earlier stages of the treatment actually increases approval, or is associated with higher level of approval, whereas as people proceed through the stages and they see how difficult IVF is and how few embryos they have in the end, they have less interest in the technology. Okay, so just the stakeholder approvals. And now let's talk about statistical consideration. Is it going to be useful for anything? And so, are we going to, so when selecting an embryo for a higher level of a certain trait or lower disease risk, is it actually going to work? And of course, we cannot do this type of experiment because we will have to wait many years to see the outcomes of most conditions of interest. We cannot wait until we see if someone develops Alzheimer's, right? I mean, you can start a study now. We have to wait until year 2100. So that's unrealistic. So we have to rely on modeling or some biobank data, as I will show, which is it's not great, but that's the only way we can tell whether it's useful for anything. Okay, so the first thing that comes to mind to a lot of people is that, of course, this is not going to work because if you think about it, the embryos that we have from the same IVF cycle, they are siblings, right? Because they all come from the same pair of parents, so they should not be so different from one another. So what's the point of doing that if all these embryos are genetically similar? So actually, this is presented like this. It's not true. So we know for over centuries, even from the time of Ronald Fisher, that the variance of a polygenic score or any genetic value within the family, like within siblings in the same families, the variance is half of the variance that we find in the population. So of course there's less variance, but there's still a lot left. Right? And for example, this is from data from one of the companies. They looked at the UK Biobank. They looked at the PRS difference for diabetes here between either unrelated pairs in gray or siblings in red. And the distribution of the difference between pairs of siblings is, of course, it's narrower compared to just two unrelated individuals, but it's still quite wide. So it's not like all the siblings, they have the same value and the differences are close to zero. So there is something to work with. It's not entirely hopeless. Okay, so now let's go to let's actually analyze the problem using statistical models that are relevant to these questions. And I'll divide the results into two. I'll start with the quantitative traits, describing earlier work that I published only 7 years ago. And then I'll move on to diseases where we have more recent results. So for traits like height or weight or IQ, the strategy that we use to study the expected gain is as follows. We started with real genomes, and then we created those virtual couples. Either we have actual couples, or we just paired people at random, and then we simulated their children. I'll show in the next slide how we simulated the genomes of the children, and then we computed the polygenic scores. Or actually, I didn't know that PGI took over PGS. I didn't realize that before I came here. So I computed PGI for the relevant trait, and then we predicted the trait of each of those simulated offspring, and then we defined the gain as the predicted value of the trait for the top-ranked embryo compared to the average of the family. Okay, then our goal was to compute like the average gain. So how did we simulate the genomes of offspring? Kind of straightforward. We do that in many studies. We start with the parental chromosome, then we simulate the locations of crossovers. We just place them at random, and then we shuffle the chromosomes based on the locations of crossovers, and then based on Mendel's law, we just select one chromosome. That's from one parent. Then we add the other parent, and this is how we generate the genome of the child or of the embryo. Okay, so so we used two cohorts, one for height and one for IQ. So we did that like 8 years ago. So these cohorts are ridiculously small, but they were useful enough for our purposes. So for height, we actually had real couples. This is why we use this cohort. And polygenic scores explain about quarter of the variance. Now the most recent scores now explain something like 40% of the variance. For IQ, explains around 4 or 5%. And that was also true at the time for in the studies that reported those scores. And now what I show you here is the mean gain in either centimeters or IQ points versus the number of embryos. Okay, so take a look at this. So this is like the main result. So take a look at these curves. So for example, for 5 embryos, so we also assume that each of these embryos will be born if it is if it will be transferred to the uterus of the female patient. So 5 embryos, that each one of them is viable, is actually quite a lot. It's quite rare for IVF patients. I'll talk about that later. But let's say we have it. So the gains that we have is something like 1 inch, like 2.5 centimeters for IQ. Real couples and random couples gave pretty much the same results. For IQ, it's also around 2.5 IQ points. So for height, of course, in relative terms, the gain is larger. It's almost the 1/2 of a standard deviation. For IQ, standard deviation is around 15 points, so it's around 1/6 of a standard deviation. So this is why, like, the way we framed the results was that it has limited utility because these gains are quite small. And as you can see, the gains do increase with more embryos. Of course, they have to increase, but they increase rather slowly. Eventually, we have diminishing returns, even with 50 embryos, which is, of course, unrealistic. This is impossible for anyone today. We only reach, for example, like less than 5 IQ points. Okay, so now we also wanted to develop a theory for that, or to think what would be maybe a formula that will represent the gain, because then we don't have to rely on those simulations, or we don't have to rely on specific phenotypes. So this is the model that we considered. We denoted the trait as the yi, trait of embryo I, and we wrote the trait like this, like as Si plus epsilon I. So S represents the polygenic index, and epsilon represents everything else. So all the genetic factors that are not in the score, all the random factors, all the environmental factors. And then the score, the index itself, okay, can also be written as a sum of two terms. The first is constant between embryos, and it has half of the variance of the polygenic score. So R squared is the proportion of variance explained by the score, and it's also the variance of the score. It's the same thing if you think about it. And C is the average, is actually the average parental polygenic score. So okay, so it's like like before the age of genetics, if we wanted to predict height, we would predict it as the average height of the parents. So here, like, kind of similarly, this part is shared by all embryos, the average polygenic score of the parents. And then each embryo has an independent component, also called segregation component, which also has half the variance. So this defines almost defines the mathematical model. No, actually, this fully defines the mathematical model for the trait. And then we can just say, okay, now we select the embryo that has the largest value of xi, and what is going to be the mean trait of this embryo. And we do the math, and then we find this quite simple expression, remarkably simple expression, which says that the average gain is proportional with some constant, some 1 point something, to R, which is like the square root of the proportion of variance explained by the score, which representing the accuracy of the score. And then for large N, it also depends on the square root of log N. So this part represents the dependence on the number of embryos. And it's quite useful, this formula, because, for example, now we can see what happens if we add more embryos. Is it really worth it? I mean, but we see, no, it only increases logarithmically, or even slower than logarithmically. And therefore, we're going to spend a lot of energy to generate those embryos, but returns are going to be diminishing. And also, it's quite nice to have this explicit dependence on R because, for example, Heresight, which is one of the companies, recently published a paper where they argued that it can now explain 20% of the variance in cognitive ability. There's some problems with the paper. Possible problems, in particular, we just nobody can reproduce it because they didn't make the weights public, and they also accounted in some way for measurement errors and so on. But without getting into the details, let's say this is 4 times more than what was previously possible. So we know if R squared was quadruples, then the gain is going to be doubled. It's just going to be the square root of it. So now, instead of 3 points, now we're at 6 points of gain in IQ. Whether this is enough to justify embryo selection, I don't want to make a judgment here. It depends on the patients themselves, whether they see it as useful or not. But it's easy to get like the order of magnitude of what we can gain from it. They're also important to mention uncertainties and limitations. So there's huge uncertainty around this number for 2 fundamental reasons. One reason is that for each family, they will generate different sets of embryos in IVF. So we don't know whether these particular embryos that the family will generate, the couples will generate, whether they will have one embryo with particularly high value of the, let's say, the IQ or polygenic score. So the embryos themselves are random, and then we also have all the non-PGI factors that will affect the actual trait. So approximately, just to give you kind of the order of magnitude, let's say we have this. Let's say we are able to increase to have like a mean gain of 5 IQ points. Okay, so maybe the company can tell can advertise it, can market the test as you have mean gain of 5 IQ points, and it will sound like a lot. But now, what is the prediction interval? What is like the 95% prediction interval for the actual IQ of the child? And if you do the math, I mean, even though we have a predictor explaining 20% of the variance, we still have 80% of the variance that's unexplained, and the prediction interval is going to remain huge. So what they can report, what the lab can report to the parents is that, yes, you have 5 points gain on average, but the interval is between 80 and 130, which is, of course, not very useful. Pretty substantial probability to even be under the, have IQ under the average, below the average. There are also limitations. Some well-known, like non-European ancestry, PGS is going to be much less accurate. Indirect effect, of course, for traits where this is relevant. Not having enough embryos is very, very important problem that I will discuss in the context of diseases coming soon. And also, we don't know whether these polygenic scores will be relevant or remain as accurate in the distant future when these embryos are going to actually develop all those traits. So, because now we are predicting IQ for people who are in their 70s, right, in the UK Biobank. So we don't know if this is going to be relevant in the environment of the future. Okay, questions so far before I transition to diseases? Yes, please. Yeah.
Do you ever have any discussion about the positive correlation between different polygenic scores? Because it seems like you are selecting the people's PRS on one dimension, but if this dimension is also negatively correlated with another desired important dimension, then it seems like there will be some kind of unintended consequence.
Don't worry, I will get to it. I promise it's coming soon. Yeah, the question of pleiotropy. I know it's important, but I'll get there. Yeah.
So I'm interested in if you have thought about potential assortative mating among couples who are interested in having this type of screening. So like that would reduce the variance. Mm-hmm. So we know for many traits the degree of assortative mating is very limited, but for like height and educational attainment, we do see the signature for assortative mating. And what are your thoughts?
Yeah, so we were also worried about it in our paper. I mean, when we saw this graph, we saw that it didn't matter, at least in that particular simulation, if you use real couples or random couples for height. So that was like one data point. But actually, it's relatively easy to adjust this this equation in the case of to the case of associative mating, indeed it reduces the gain degree that's proportional to the correlation in the correlation of the trait between the parents. That Alex Young helped me with that derivation. Associative is rather complicated, so thankfully, at least in this case, it ended up being relatively simple. But it's a consideration. If it's a trait that's, I mean, all the cognitive traits like education and cognitive ability and all that, I mean, we have to be very careful with those estimates because of all the complications with confounding and so on. Okay, so now for diseases, it's a bit more complicated because the trait is binary. A disease either exists or not, just approximately. So we used a common model. You may have heard of it. It's called the liability threshold model. It's a model to relate the genetic risk to the outcome, to the binary outcome. And the idea is that we assume that each disease has an underlying continuous liability. So this liability is unobserved. We cannot measure it, but we assume it exists. And we also assume that whenever individuals have liability that crosses this threshold due to both genetic and non-genetic risk factors, they become affected. So we have this concept of disease threshold. And what goes into the liability? Liability has a genetic component, and then it also has non-genetic or environmental component, and we assume all of these components are normally distributed, and overall the liability is a standard normal variable. So it's easy to specify where the threshold would be. And this way we can take the genetic values of the embryos and we can translate them into risk or probability of being affected with the disease. So I won't go into all the mathematical details. It's not enough time to cover it here, but I'll just tell you what our modeling framework looks like. And we assume we are selecting for a single disease. So how does it work? We assume all those inputs. So we assume that there is a certain number of embryos that are available for selection. We're able to in our most recent publication, we are also able to take into account the live birth rate. So whenever there is an embryo, we assume that it may, if we transfer it, it may not be born because no pregnancy or miscarriage. And then we need to specify the disease prevalence, the PRS accuracy or proportional variance explained, how embryo is selected, either the lowest embryo or just excluding embryos that are very high risk. And we can also condition on the parental PRS or the disease status of family members, like either the parents or other relatives of the embryo. Even an already born child, we can also incorporate. So we have all those variables, and from all of them together, we are able to model the distribution of the PRS in the sibling embryos. And once you have the distribution of all of them, we can also find what is the distribution of the PRS of the embryo with the lowest risk, the embryo that will be selected. And from those two, we are able to compute the risk of the selected embryo, which in the simplest case, it comes out as this integral, which we can solve numerically. It's very easy, and we can also compare it to the risk of a random embryo. And now when we have the risk of the selected embryo and the random embryo, we can compute risk reduction. So we can compute the degree to which risk has decreased, either absolutely or in relative terms, or we can also compute the number needed to screen. So the number of couples that would have to screen their embryos to avoid one disease case, just the inverse of the absolute risk reduction. Okay, so this is what we did, and you don't have to worry about mathematical details because we have a very nice and user-friendly web app. This is just accepted to bioinformatics a few days ago. So here you can specify like the model for how many embryos exist, if it's a fixed number or this binomial number, and probability of live birth, and what do you want to show on the x-axis, if it's the number of embryos or PRS accuracy and so on, and specify the parameters, and then you can generate plots of the risk reduction versus any parameter of choice. And in another screen, you can also specify the disease history of all family members. So it's quite nice web app that you can access here or in this address. Okay, but now what do the results look like? Okay, so now let's look at what do we expect to see. So what I'm showing you here is the relative risk reduction versus the number of euploid embryos, assuming that 0.4 are born. And we look at an example of a disease like Crohn's disease with prevalence 0.5%. And we look at two values of the PRS accuracy, either 5% or 10%. For Crohn's, that's pretty much the order of magnitude of what polygenic risk scores achieve in previous studies. And let's look at the numbers. So you can see with 4 embryos, the risk reduction is between 20 to 30%. For 6 embryos, it can be 40% or even 30%. So risk reductions are quite large, at least in relative terms. For schizophrenia, again, numbers are similar with 6 embryos, and with a good predictor, we can reach risk reductions of around 40%. And this is even taking into account the possibility of failure of the embryo to be born. So these risk reductions, they are not negligible, I would say, because once the child is born, there's no way to reduce risk for those conditions by 40%. We just don't know of any intervention that would achieve such risk reduction. So these are definitely meaningful, and kind of historically, we did the studies and we found those very limited gains for traits like IQ. We thought, okay, this is like the end of it because there are all those ethical problems, and then it's not even useful. So we'll just show that it's also not useful for diseases, and then I'll move on to do some back to population genetics or something. But then we actually found that risk reduction can be large. So then we kind of changed route and we started studying all those, in more detail, all the ethical and social and clinical issues. And also, it's important to understand the limitations, because this is really the best case scenario. It's not so clear when it is going to be valid. Okay, there are two things that I did not address so far. First of all, this is based on modeling, so I don't know if modeling is it depends on a lot of assumptions, like the liability threshold model, mathematical assumptions, some of them for convenience, but we also want some data. And also what happens if we select for multiple conditions at once, which is the question that kind of arose earlier. So the alternative is to look at the siblings in biobanks, and the idea is to look at pairs of siblings and to imagine that these are embryos, okay? And we need to select one of them based on either at random or based on having the lower risk for one disease or for a combination of diseases. But then these are not embryos; these are adults, so we can go to the biobank and we can see what happened to them. Like, who got sick and who didn't, and then we can compare the risk between those two selection strategies. So this is a very important idea. This is one study by one of the companies using same-sex sibling pairs in the UK biobank. And here they selected jointly for 11 different conditions. And you can see the risk, like the baseline risk for random selection in orange. And in yellow, you can see the risk was based on PRS, with PRS-based selection. And you can see risk reduction across all diseases, even though they were selecting jointly for all of them. And the relative risk reduction, they look quite impressive. But also one important point to note here is that the absolute risk reduction can be quite small for the rare conditions. So type 1 diabetes, there is impressive reduction of 1/3 in the risk, but you can see in absolute terms, it's barely noticeable. We recently started an attempt to reproduce these results in FinGen with, remarkably, they have almost 43,000 sibling pairs. So we looked at 73 phenotypes, and that helped us to address a couple of questions. Here we looked at theoretical risk reduction when selecting based on a single disease risk versus the observed risk reduction, which is just looking at those sibling pairs, and selecting one of them and looking at the risk. And we can see very good agreement between theoretical and observed, like empirical risk reduction. We can ignore these outliers because the confidence intervals are quite large. And we also see that kind of the median is around 10%. So with the given polygenic scores that we have right now, at least in FinGen, this is what we can gain when selecting for a single disease. What happens when we select for multiple conditions? So this is the distribution of risk reduction when we select based on the average PRS for for all 73 phenotypes. Okay, so no, these are unpublished results. So you're going to, I don't know if you're going to post it in the website. This picture. Maybe can you take a picture of another slide? not this particular one. It's the only result that's actually a bit sensitive because it's not my data. Yeah, sorry. So what you can see is that obviously the risk reduction per phenotype per disease is now around 5%. It's less than what we had before, but it's still more than zero. We still have risk reduction across almost all conditions. Of course, for some conditions we actually increase risk. I mean, there's some randomness, but also importantly, we also looked at 66 other conditions that we did not screen for, and we can see that the risk reduction in pink here is about the same. So we don't have to be worried so much about about conditions that we did not screen for, because pleiotropy is mostly positive, or either absent or positive. So if we select an embryo for low risk for one condition, usually it will lower the risk also for other conditions. And we don't have to worry so much about this issue. Of course, there are some specific cases, like for example, if we select for low risk of obesity, we increase the risk of anorexia, for example. But so we have some very, very specific pairs of conditions that we would like to be careful about, particularly with cognitive abilities. But generally speaking, it's not a major concern. Okay, so why did I show kind of limited gains for traits, but more substantial gains for risk reduction, for disease risk reduction? So the key point is my intuition, the way I think of it, like my intuition is that this is because of dichotomization. So let's think about IQ, for example, normal distribution, the mean at 100. Now let's dichotomize IQ. Let's imagine that everyone with IQ under 70 is affected, maybe call it intellectual disability or whatever, just for the purpose of this exercise. So now let's rethink about selecting selecting an embryo based on the PGI for IQ, and let's see what happens after we dichotomize. What would be the risk reduction? So under random selection, it's just the tail of the distribution. This is the risk to have for a random person to have a intellectual disability. What happens when we select based on genetics, based on having the largest PGI for IQ? Then we shift the distribution to the right a little bit. Let's say just 2.5 points. Okay, so like very small quantitative gains. The average IQ will increase by just a little bit, right? But what happens to the tail? That actually the proportion of people with IQ under 70 is reduced by 33%. So the risk reduction is quite large after we dichotomize, because if you think about it, like a lot of those people who were affected, they had IQ very close to the threshold. So if we move everything just a little bit, a lot of people now are no longer under the definition of being affected. They were kind of rescued, so to say. But that also raises the question whether which I'm not going to answer, but just going to raise the question whether all those impressive risk reductions, maybe 40% or 50% or whatever, they just represent kind of artificial dichotomization of the diseases, which is not really, maybe for diabetes, we have the HbA1c, and we just define everyone above a cutoff as affected. So maybe it does not really reflect the improvement in the underlying health. Okay, but that's a point for thought for later. But now I want to go back to the point of the number of embryos. How many embryos are available, like in the end, for selection? And do typical patients, IVF patients, do they have enough embryos? So we have recent results this is a manuscript we posted a few weeks ago that argue that the answer here is clearly no. IVF patients do not have enough embryos to achieve meaningful gains using polygenic embryo screening. So we used something like 7,000 IVF cycles from a clinic in Italy, and risk reductions, which were close to 50% before, are now, when we look at various values of the prevalence or R squared, now they're close to like 2%, 4%, at most 5%. So like the best case scenario is 5% risk reduction for a condition that I convinced you earlier that if you only have like 5 viable embryos, you can reduce risk by 50%, but it's just extremely rare for infertility patients to have that many embryos. Usually they have 1 or 2 embryos. If they have 1 embryo they cannot select from, very often, actually most of the time, they don't have enough embryos at all. They don't have any child from the IVF cycle. So risk reductions are going to be 0. And this means that if someone, maybe particularly if you read like the marketing materials from those companies, they tell you you're already doing IVF, you're already doing PGT for aneuploidy, why not use the data to select embryos? Then it's misleading in the sense that if you came to IVF because of infertility, most of the time you will be much more concerned about having a baby, a single child, rather than having an optimized child. So this is probably a distraction for this type of patients. Let me skip that for the interest of time and let me talk for maybe 5 minutes about possible clinical harms, and then we can open into more discussion. So what are the considerations of healthcare professionals? They're worried about multiple harms to patients and their children. The main harm is unnecessary exposure to IVF, because if, as I just said, like for people already doing IVF, this is not so relevant because they don't have enough embryos. So the only people who will benefit from it, they don't need IVF because they can reproduce, naturally. So going through IVF, at least currently, is expensive, it's painful, it's stressful, takes a lot of time. This is an experience that we don't want people to go through unless they really have to. Another problem is that if we, particularly for infertility patients, if we start ranking the embryos and say, okay, these embryos should be deprioritized, then patients may not use them, and then they will have to do more cycles, or they will not, maybe they will end up not using any embryo, and they will end up not having children. So this will harm their reproductive goals, and they will end up with IVF failure instead of just having a perfectly healthy child with whichever embryos they already had. So this can confuse patients and lead to more harm than benefit. Soon I'll spend more time on these 2 points about patient experience, genetic counseling, marketing pressure, choice overload. These are important considerations. I'll talk about them in the next slide. There are possible harms for which we simply have no data right now. They're not very plausible, but worth studying in the future. One is that embryos with good polygenic scores for the target disease or trait will have lower competence, so they will not be they will have lower live birth rates, for example. Another question, maybe this is more plausible, is a long-term, particularly psychological impact on the parents and children because of going through this test. I don't know. There's no data on that, so maybe so this is something worth studying in the future. Where do we expect almost no harm, despite concerns that some people raised? First, increasing the risk of another disease, as I mentioned earlier. Then some people are concerned about having to do the biopsy to the embryo, which is otherwise not required, but that's actually okay. It does not harm the embryo. It does not affect the pregnancy, maybe very, very minor impact. And also some people are concerned about loss of genetic diversity, but here we also have some results, and it's also obvious because of the polygenicity of most conditions that polygenic embryo screening, even if everyone in the population is going to use it, is not going to substantially change allele frequencies. The change is going to be negligible for any specific variant. And also maybe it's a good thing. I mean, if we lose a lot of risk increasing allele, maybe it's a good thing. So why worry about it? Okay, so I talked about choice overload. So this is the report from one of the companies, from Orchid. And actually, the other companies have even more complicated reports. So this is the list of the conditions that they screen for. They show the population average, they show the embryo, they show some percentages here. I mean, you guys are all, professional geneticists, expert in polygenic scores, and it's going to take you, a few minutes to figure out what's going on here. And and what's going on with all of these conditions. And now that's only your embryo A. Okay, so now you also have embryo B and C and D and E. And then you have to make a very important decision of who is going to be born. It is going to be difficult. So this is very likely to overwhelm the patient. There is already some anecdotal evidence that some patients just quit IVF because they just didn't know what to do. Of course, like all those early adopters from the Silicon Valley, I mean, they just only waited to see those reports. They downloaded everything as Excel files. They went home and they did all those formulas, to select their baby. But for the average patient, this is going to be complicated and overwhelming. In terms of counseling, how to provide counseling is not a trivial question. As opposed to PGTM, going back to your question before, I mean, here we have uncertainty. We have a probabilistic model to explain. It's more difficult to explain risk, and even risk reduction is difficult to explain. So, for example, this is again from ORCID. This is how they present the results for protection from schizophrenia. They do present the absolute risk, but they also focus on the 32% relative risk reduction. Okay, but there's also another way to present the same data, right? Selected your embryos to increase the risk of having a child without schizophrenia, by these numbers, and of course, this is much less impressive. So it's really it's all very susceptible to marketing pressure to be applied on the parents. And providing unbiased counseling is going to be not so easy. And if let's also look at the evolution of marketing just to demonstrate this point. So this is LiveView or Genomic Prediction, the first company. Choose your healthiest embryo, which I don't know, maybe can be acceptable. ORCID, have healthy babies. Now with Herasite, they're already into IQ, so they have this IQ calculator. Okay, you have 10 embryos. You can increase your highest embryo will have IQ 107. Of course, they show the lowest also to make it more impressive. And then we have Nucleus, which recently had a campaign in the New York subway. You may have heard of it. And this is like intentionally eugenics. Of course, they wanted to have the bad press because it gave them a lot of attention to the company, and well, I mean, I know some people. We can come up. Going back to the ethics question of eugenics. Eugenics is complicated, and there are some ways to defend it. But I think probably every one of us, feels somewhat uncomfortable at least. Seeing these advertisements. So marketing pressure is a problem. There are some other clinical considerations, probably short term, but some are quite important, like how to get all those genetic counselors. It's extremely difficult to find genetic counselors. Where to store all those embryos. What about patient-clinician conflicts? One thing that people don't talk about enough is what happens when the ranking changes over time, because now we have a new GWAS. So imagine parents transferred one embryo, it is born, and then new GWAS comes out, the lab re-ranks, and then, oh, sorry, your embryo is now actually has the highest risk, the one that was already born. What happens when another lab gives a different ranking? Complicated questions, liability for always difficult. They're probably all solvable, but difficult questions for implementation. This is also one of and the main thing is for clinicians, at least in the United States, most of them did not figure out how to actually make money out of this. So this is why it's not so widely offered, even though these companies exist. And just to wrap up, important point to remember is that in the end of the day, all the benefits and harms are patient-specific. So polygenic embryo screening, maybe when you read the article in the newspaper, maybe it sounds like one thing, but it's actually multiple types of screens depending on who is being screened and what are the circumstances. And the considerations can be very, very different. And between people who are already going IVF, people who have no problem whatsoever, maybe people with a history of a disease, maybe that's a group where risk reductions are large and there are relatively not too many harms. So maybe that's a group, that's what we think at least, that maybe that's a group to start studying polygenic embryo screening more seriously because this is probably the most promising subgroup. Okay, so with that, I'll acknowledge many collaborators, particularly Todd Lentz and Liraz and Gilad from my group, and also other collaborators. We have this review paper from 2 years ago that summarized most of what I told you today, and happy to continue the discussion. I'm also staying here until tomorrow morning, so if anyone wants to have a really deep conversation, you're very welcome.
Do we have data on? So you have the data in the fertility patients, but like what fraction of infertility patients end up using like donor eggs, and what's the distribution of embryos in that population, or even just among like if you randomly selected a person? Like, do we have any sense of what the distribution of viable embryos come out of those groups?
Yeah, so we have in that preprint, we also have data from 2,000 egg donor cycles. I don't know what fraction of IVF patients use egg donation, but for egg donors, we saw many more embryos and much larger risk reduction. Risk reductions were now in around 25%, something like that.
Many more meaning like, what was it, maybe 10?
I mean, depending on how you define it, like how many, like blastocysts or euploid blastocysts. I mean, it depends on how you define it. But so I don't want to go into the numbers. But the risk reduction, like in the end, were over 20%. So that's much more promising. But that implies the implication is that it's really going to be useful for people who have good fertility or are younger. Who don't require IVF to begin with. This raises all the other ethical questions and clinical questions.
It's more common for young women freezing their eggs, right?
Yeah, but most women who freeze, they do it when they're already closer to 40. But yeah, that's a subgroup we didn't have data on, though.
Thanks for your talk. The way I would summarize is in a sense you're saying like there's of course the big ethical question, and on the other hand there is the question of like the way that these companies are currently selling it. Does it even work? Is it what you could call like something of a viable product, or is it just very expensive snake oil in a sense?
Yeah. So what I would like to emphasize is it's not snake oil. As opposed, I mean, there was like a paper came out in Nature Human Behavior just yesterday about the subject. There are some papers from even from professional societies saying, this is not going to work, for various reasons. For example, there's not enough variability between siblings, which is a myth, or things like pleiotropy, which is a myth because like the data shows otherwise. So I want to emphasize that based on all of the evidence that we have so far, this is not snake oil. At least even for traits, if we have good predictor for the trait, which we may have one day with larger GWAS, or maybe with a new way of computing polygenic indices, we could have some gains. So some people say, okay, polygenic scores are not, we don't know the causal variant, so it's not going to work, or some arguments like this. I think they're incorrect. So there is potential to lower disease risk or increase traits. But there are but what I want to also emphasize, there are a lot of limitations, practical limitations that we should not be overlooking, and the companies sometimes they kind of sweep them under the rug. And we also have to think about the ethical considerations, where I don't want to make a judgment like what is right or wrong. I think it's possible that every society will decide something else based on their own set of values.
Yeah. So to me, the central question on that point is like, which you alluded to, is like how large is the effect size, right? And this what you show with, for example, the schizophrenia risk. Like we can say like it's a 0.3% reduction, or it's like you don't get the disease from 99.1 to 99.4. And I think a big part of the question is like, is that a large reduction risk as compared to the cost? And so what strikes me about your talk in general is like, as economists, we have tools to understand that. We constantly do the cost-benefit analysis of all types of medical treatments. And that's a way to ask yourself, like, can you justify the costs versus the benefits right? Despite the ethical questions, you can say statistically we can quantify some benefits. And yeah, it just strikes me. So is there like no literature at all that puts this in like a classical cost-benefit analysis perspective?
I fully agree, because when we say reduce risk by 20%, like is it large or small? It's like always relative to something, right? And the only way to measure it unbiasedly is in the value of the dollar, like the dollar value that it saves you, right? I mean, that's the only, and then you can compare it to the cost. So I fully agree that that's the main way to actually say whether this is something that should be implemented or not. We didn't get there yet. Patrick and I and Leandro also have been talking about that. Maybe we'll get there this year. But that's a very important open question, and I fully agree. And great to also hear that you also raised that as the way forward.
Instead of having, you cannot give me a number on that. You cannot say.
So I did do some back of the envelope calculation that showed that you kind of break even with risk reduction, but that was very, very rough calculation. So I wouldn't want to say more before we have.
Right.
More.
Thanks. I'll look out for it. Thanks.
Yeah.
Thank you. That was fascinating. No, I was curious about where do we, what is the stage of like selection of eggs and sperm, like because that probably for many cases, even the couples that have fertility problem, one of them may not, right? Sort of. So you would have many more options, but I imagine that the technology is sort of not as far.
Yeah, we don't know how to genotype the egg or the gametes, the egg or sperm, because it will be destructive. That's the problem. It's very simple. So we can only test. The reason why we can test the embryo is because the embryo already multiplied. So the embryo has like 150 cells at this point, and we can just take a few without causing any harm.
I see. Okay. Yeah. There's an argument from James Lee against embryo selection that if people start reproducing without having sex, eventually there will be a selection against sex. People will no longer be predisposed to fall in love or even be aroused by other people. Temporary concerns about are we a little bit smarter or not in the future? Doesn't the long-term risk of us losing our humanity and capacity for love seem like the biggest problem of embryo selection?
Yeah. So, well, I mean, those long-term predictions, of course, I cannot say anything smart about them, but yeah, I mean, one of the companies like Orchid, for example, their CEO markets the polygenic embryo screening. I mean, like the words she used is sex is for fun, embryo screening is for babies, and of course there was a lot of criticism about that, but I'm not so worried about the evolution of love and all that, because I think we're talking about evolution takes several generations, and who knows what we are going to have in 50 years. The world is going to look like very, very different. So that's not my concern, but it is concern for a lot of people. If reproduction is now going to be medicalized, that's not something that people want. But I think I gave it some thought to this question. But on the other hand, like labor, for example, used to be natural, and now it has been medicalized, right? So I guess other things have also been medicalized, and maybe it's good. So maybe it feels very weird right now, but maybe we'll just, like in 20 years, maybe we'll just get used to it. I don't know.
Thank you very much.
I have two questions.
Yeah.
First question is a bit difficult for me to articulate.
Okay.
But whenever we want to bring some kind of approach into the clinical setting for some translational impact, or when we talk about policy, we have these metrics to quantify at the population level how big impact this would have, like to reduce disease prevalence by a certain percentage, for example. But you also made an important point, which I agree with in your talk, that the difference between this and, say, eugenic activities we've had in the past century is this is more personal. Right, the family comes in and they need to make the choice. This is not some kind of a national program that affects everybody.
Right.
But is it supposed to be some kind of a betrayal if we start talking about, if we do this at the national level, you would reduce Alzheimer's by 5% or 20%?
Yeah.
Is it the intentional choice to focus on, for this specific family, the variance of prediction result is going to be high. Because in your figures, for example, when you estimate the population level average, the confidence intervals are very narrow, right? But it becomes a much more unpredictable fact if you focus on individual families.
Yeah, that's the point I mentioned regarding IQ, that eventually like the prediction interval is like anything between 80 and 130. So for the given family, it's almost useless when you try to predict a quantitative trait. For risk, it's already probabilistic. So you can say, okay, your risk was 20%, now it's 12%, for example. But I think you make a good point regarding if we think that this is very useful, and let's say if we now say, okay, everyone should do it because it's going to reduce the healthcare cost and it's going to improve the health of the population, and so now it's going to become mandatory, maybe, and then we are going back to eugenics. So there is a bit of a problem here. If it ever becomes so useful that everyone will have to do it. Yeah, that I don't have a good answer. But that's maybe like the slippery slope that people are concerned about.
So like, for example, during the talk, I was thinking of a specific example. Let's say someone proposes a policy to make sure all genetic embryonic screening effort is covered by insurance, right? National law.
Yeah.
One way to look at this is now you don't have that accessibility problem. So rich or poor, everybody can access this equally. In some way, you can argue that this is reducing some of the ethical concerns. Right. But then does it make it full-on eugenics that the entire nation now is exposed to this?
Yeah.
I wonder.
Yeah, I think you're right. I think it's a concern. Yeah. Yeah, but it's similar to other healthcare interventions. But maybe we're less worried about vaccines and more worried about eugenics, about genetic interventions. We are very worried about genetic interventions because of the history of eugenics. Maybe you shouldn't be so worried about it. That's one argument. It's very difficult to understand from what I've read, like what exactly in the 20th century, what exactly made eugenics go so bad? Like what exactly made it so horrible? Which components specifically? Is it the coercion, or is it the fact that it was administered by the government, or is it the fact that it was genetic intervention? Or I don't know. Can something like this ever happen again? These are questions that are difficult to answer, and therefore it's it is a concern, and we don't have good answers right now. Yeah.
Thank you for your talk. So I'm just wondering, do we have any data on what proportion of IVF treatments are not for infertility? I know there's a market in the US for, gender, right?
Yeah.
That people go through IVF because they want the baby at a certain gender. Do we know how common it is, and is it growing over time, or is it going to grow as this technologies advance? Do we have any sense of how big this market is?
Do you count PGT-M as infertility? Like for cystic fibrosis, for example, there's no well, maybe it's a bad example, but for some other monogenic condition, do you count that as infertility?
I guess it's a third.
Yeah.
I guess I would like a third.
Yeah.
So
it depends on the country. So in the United States, there are not so many founder variants. So PGT-M is not very common. So it's mostly infertility and some sex selection. I don't know the numbers, but my understanding it's not a huge proportion of those cycles. For one reason, because it's very expensive in the United States,
right.
And different countries regulate PGT very, very differently. So there's no single answer to that question. Mm-hmm. But I think even in the United States, the fact that sex selection is possible, it didn't. There's no huge demand for it.
There's no huge demand.
No.
Well, it depends on level of income.
Yeah, but
huge, right?
Again, I don't know the precise numbers, but I can't imagine it's more than 5% of cycles, or probably much less. So you don't see hundreds of thousands of people each year. Or I mean, among the people who are having babies each year, it's probably a tiny proportion of them going through sex selection. Yeah.
Let's all thank Shai for a great talk.
Thank you.
I think we don't have any more announcements except to thank you all for coming. You'll be getting a survey of telling us what you liked and what we can do better next time. And I think I'll just wish you safe travels and hang around here and talk to Shai some more if you'd like. But safe travels and see you hopefully next year.